Welcome to your deep dive. Today, we're really plunging into a topic that's, well, it's fundamentally reshaping the world around us.
Hmm.
The profound impact of artificial intelligence on the future of electronics. From the tiniest components right up to these massive complex systems.
It really is. It's a subject that touches pretty much everything you interact with daily, often without even realizing it.
Right.
I mean, the chips in your phone, the networks powering our cities, the autonomous systems starting to pop up everywhere. It's all underpinned by this rapid evolution we're seeing.
Absolutely. And you've brought us, well, quite a stack of sources here. It looks like a mix of articles, some pretty detailed research papers, and key industry reports, too.
Yeah, quite a collection.
And they all seem to be pointing towards like a completely new electronics revolution, an era where AI isn't just using electronics anymore.
Exactly. It's becoming a core driver, even a creator
Yeah.
of the electronics themselves. That's the big shift.
Okay, so our mission in this deep dive then is to take these sources, really unpack them layer by layer,
Dig into the detail.
extract the most crucial insights, those key nuggets of knowledge, and try to truly understand what this powerful AI imperative, as some sources call it, really means, for the future of silicon, components, how electronic systems are actually going to work.
That's the goal, to piece together the puzzle from what these different reports and papers are telling us.
So let's jump right in. Let's unpack this massive transformation. We need to look closely at how AI is influencing, well, pretty much everything in electronics.
From the ground up.
Right, from the fundamental foundation and market demand all the way through the actual design process, fabrication.
And even enabling entirely new ways of computing that honestly seemed pretty theoretical not that long ago.
It sounds like a really complex story, lots of interconnectedness, rapid change, and probably some significant challenges along the way.
Definitely. It's a story of deep connections, incredible speed, and yes, some very real hurdles to overcome.
All right, let's start at the beginning then. Section 1. What the sources are calling the AI imperative. What's the core concept here?
So the sources, particularly Source 2 and Source 1, they really established that AI has moved way beyond just being another application that electronics run.
Okay.
It's become a foundational technology.
Yeah.
It's fundamentally driving a paradigm shift across the entire electronics and semiconductor landscape.
So think of it less like a program running on the computer.
And more like the engine that's redefining the very nature of the computer itself.
Yeah.
That's the core idea.
Got it. So it's no longer just about making electronics for AI,
Right.
but making electronics because of AI. The demand is pulling the industry.
Yeah, exactly. And the primary catalyst for this, well, unprecedented level of growth and innovation we're seeing is the absolutely massive and frankly seemingly insatiable demand for AI processing power.
Right, the compute demand.
Source 1 makes this crystal clear. AI's hunger for computation is the main engine driving growth right now. As AI technologies get deeply embedded in more and more applications, from huge data centers training these giant language models,
Like the ones we hear about all the time.
all the way down to the tiny microcontrollers in the consumer electronics you use every single day. There's this escalating need for electronic components that are not just powerful, but also highly specialized. They need to be optimized specifically for AI tasks.
That makes sense. I mean, the kind of math needed for deep learning is really different from running a spreadsheet or a web browser, right?
Completely different. Highly parallel, lots of matrix multiplication.
So this isn't just needing more chips overall, it's needing different kinds of chips, specialized ones.
Precisely. It's really marking a new epoch for the whole semiconductor sector. AI isn't some peripheral influence anymore.
It's central.
It's the core driver. It's fundamentally changing how electronic systems are conceived, how they're designed, manufactured, and even how they get deployed and used out in the real world. It's just driving this incredible acceleration in the industry.
And this brings us to what some of the sources describe as a symbiotic relationship between AI advancement and hardware evolution. How does that cycle actually work in practice?
Yeah, they often call it a virtuous cycle, and sources 3 and 4 lay this out pretty well. Basically, AI algorithms and models are constantly advancing. They're getting more sophisticated, more complex.
Bigger.
Bigger, exactly, and much more demanding in terms of computational resources. This immediately pushes the boundaries of the hardware we have now.
So AI is saying, I need more.
It requires components that are faster, more specialized, and crucially, significantly more energy efficient, because the scale of these computations is just mind-boggling.
Okay, so AI basically tells the hardware industry, look, I need more power, I need it faster, and frankly, cheaper per calculation, and the hardware guys just have to respond.
That's definitely the initial impulse, yeah.
Yeah.
The demand from AI creates immense pressure, but also huge opportunity for hardware innovation.
Right.
But then, and this is the other side of the cycle, breakthroughs in semiconductor tech and circuit design, new materials, new chip architectures, better manufacturing processes, they turn around and unlock new capabilities for AI. Better hardware enables more complex calculations, allows for even larger models to be trained or run efficiently.
And facilitates more sophisticated AI applications that maybe just weren't computationally feasible before.
Exactly. You couldn't even dream of running them on older hardware. Semiconductors are the absolute bedrock here, providing the physical layer for all this processing.
But the traditional general-purpose processors, like the CPUs that were mostly designed for running desktop apps or standard server tasks, they aren't really cutting it for today's cutting-edge AI workloads, are they?
Not for the really demanding stuff, no. Training state-of-the-art large language models, processing real-time sensor data streams for autonomous systems, doing complex inference right there at the edge.
Yeah.
These things require an immense amount of computational throughput that general-purpose CPUs just weren't built for. It's a different kind of compute.
And that's what spurred the massive development of specialized hardware, the stuff specifically tailored for AI.
Exactly.
Like the GPUs we hear so much about.
GPUs were definitely the first major wave. They were initially designed for graphics, right?
Right, for games.
But they turned out to be incredibly effective at the kind of parallel computations AI needs. But it goes much further now. Google developed their tensor processing units, TPUs.
Right.
And then there's this whole rapidly growing ecosystem of custom AI accelerators, often called ASICs, or application-specific integrated circuits. Source 4 highlights how these are meticulously designed, right down to the silicon level, specifically to handle AI workloads with the best possible performance and efficiency.
Okay, and here's where it gets really interesting. As the source has mentioned, it's not just a simple one-way street where AI demands hardware. AI itself is now actually participating in creating this next generation of hardware.
That's a key insight, yeah, from sources 3 and 4. AI is being used extensively now in electronic design automation, or EDA.
That's the software used to design chips.
Exactly, the whole suite of complex software engineers use. And AI is also being deployed in the cutting-edge field of AI-driven materials discovery, literally finding the new substances these future chips will be made from.
Wow.
This integration creates a much tighter, much more rapid feedback loop. Advancements in AI software and hardware capabilities don't just passively enable each other anymore.
They're actively boosting each other.
They mutually reinforce and accelerate each other's progress. It's becoming a really fast cycle.
So, hold on. We have AI helping to design the very chips that will run the next generation of AI. And those new chips are so much better that they enable even more advanced AI, which can then potentially help design even better chips and maybe even find entirely new materials for them.
Precisely. It's an exponential feedback loop, and it's driving innovation at a speed we haven't really seen before in this industry. Future breakthroughs in AI are increasingly linked to, and probably going to be enabled by, innovations in hardware that was, at least in part, designed or maybe even discovered using AI itself.
That's incredible.
And this isn't just about making existing tasks faster anymore. It's extending to the creation of fundamentally new functionalities, entirely new computing paradigms, and even new capabilities in material science.
We'll definitely need to dive into those new paradigms later. That sounds fascinating. But first, let's look at how this AI imperative is reshaping the actual market. The sources have some pretty impressive, maybe even eye-opening numbers here about the sheer scale of this change.
They certainly do. Source 1 uses the phrase AI's voracious appetite for compute. And says it's dramatically reshaping demand across almost every single electronic component category.
Okay, let's start with semiconductors overall. What's the big picture looking like?
So Source 1 and Source 6 provide some really compelling data here. The global semiconductor market is seeing a significant surge, especially after a bit of a downturn recently. Revenues reached an estimated $627 billion in 2024. That's a robust 19% year-over-year increase.
19%. Wow.
Yeah. And looking ahead, it's projected to grow another solid 15% in 2025.
That's well beyond typical industry growth rates, isn't it?
It is, yeah. And it's overwhelmingly attributed to this escalating demand for AI-enabled devices and applications across pretty much all sectors. Source 8 gives an even broader forecast. They project the market expanding from around $681 billion in 2024 to a staggering $2062 billion that's over $2 trillion by 2032.
$2 trillion?
Yeah. That represents a compound annual growth rate, or a CAGR, of nearly 15% over that whole period.
Incredible.
These numbers just underscore that semiconductors truly are the foundational backbone for all this AI processing power, and AI is fueling their expansion like nothing we've seen before.
Okay, what about memory? Specifically, high bandwidth memory, HBM. I keep seeing that mentioned as being particularly critical for AI.
Memory is experiencing absolutely phenomenal growth, precisely because of these AI demands.
Yeah.
Source 1 points to substantial expansion in the DRAM market, and that's heavily influenced by HBM demand. Get this, a massive 76.8% growth in 2024 alone.
76% in 1 year.
Yeah, and they anticipate a further 25% increase in 2025.
Yeah.
These are just huge numbers that highlight the unique pressure AI is putting on memory interfaces.
Why is memory, and specifically HBM, so critical for tasks like training those large language models?
Source 1 and Source 6 explain why this matters so much. HBM is critical for providing the super high bandwidth data storage and processing needed by these large AI models, especially generative AI.
Right.
These models have vast numbers of parameters, billions, sometimes trillions, and they require moving immense amounts of data very, very quickly between the processor and the memory modules. HBM is specifically designed to handle that kind of speed and bandwidth much better than traditional DDR memory.
So it stops the processor from just sitting there waiting for data.
Exactly.
Right.
It prevents the processor from being starved for data, which is crucial for efficiency.
Okay, so semiconductors overall are booming. Memory is essential, particularly HBM. What about the chips designed specifically for running AI workloads, the GPUs, TPUs, those custom AI chips?
This is where the growth figures get truly exponential. The market for these AI-specific chips, GPUs, TPUs, custom ASICs, tailored for AI, is projected to expand by an astounding $389 billion between 2024 and 2028.
$389 billion, just for those specific chips.
Just for that segment. Source 1 points out that this translates to a CAGR exceeding 68% over just 4 years.
68% CAGR. That's explosive growth.
It really is. It's an incredibly hot segment. Source 1 gives a concrete example of this commercial impact. Marvell Technology reported $535 million in AI-related revenues in just one recent quarter. It shows how quickly this translates into real revenue for companies focused here. These chips are meticulously designed and optimized, specifically for the unique, highly parallel demands of AI training and inference workloads.
Okay, what about the components that collect the data AI needs to learn from and operate on? Sensors, for
The
instance.
sensors are absolutely pivotal, yeah.
Yeah.
Source 1 highlights their essential role. They enable the collection of the vast amounts of real-world data that AI algorithms need to process images, sound, environmental data, movement data, you name it.
Right, the eyes and ears for the AI.
Exactly. The discrete semiconductors and sensor segment, while smaller overall than compute or memory, is showing steady improvement. Growth rates are around 7.8% and 7.4% respectively, and that's directly tied to AI applications needing to perceive the environment.
And where are we seeing this demand for AI-driven sensors most strongly?
It's becoming ubiquitous, really, in consumer electronics, obviously, for things like facial recognition or voice assistance, but also heavily in automotive systems, especially for advanced driver assistance systems, ADAS, and the move towards autonomous driving, which rely on a whole sophisticated suite of sensors.
LiDARs, radars, cameras.
All of it. And increasingly in industrial automation, too, where sensors feed data into AI systems for things like predictive maintenance on machinery or quality control on production lines. Sensors are integral to enabling devices to perceive their environment and then respond intelligently.
Okay, moving on to more fundamental building blocks like integrated circuits, ICs, often just called logic chips. What's the impact there?
ICs are absolutely essential. They form the core logic needed for constructing the intricate digital architectures required in complex AI systems.
The brains of the operation, in a way.
In a way, yes. This segment is forecasted for robust growth as well, with a 20.8% increase projected for 2024, according to Source 1.
So very strong growth.
Definitely. Their versatility makes them indispensable right across the board. From integrating processing units and memory on a single chip in power-constrained edge computing devices, all the way to forming the complex logic structures in massive data center processors.
And even seemingly simpler components like connectors, switches, relays, they're feeling the AI influence too.
Yes, even those electromechanical components play a really crucial role. Source 1 explains they're vital for the seamless operation, the high-speed connectivity needed, and the efficient power delivery within these increasingly complex and, frankly, power-hungry AI systems.
So connectors need higher bandwidth.
Higher bandwidth, higher power handling. Switches and relays need to manage power distribution more effectively. Source 1 links their growth directly to the overall trend of integrating more complex AI hardware into systems. The sheer complexity and scale of modern AI systems necessitate advancements across the entire bill of materials, not just the main processing chips.
Okay, so putting all this together, AI isn't just increasing demand across the board, it's fundamentally reshaping what components are considered critical and where the actual value lies in the electronics market today.
That's the key synthesis from Source 1, yeah. AI is driving a definite shift in the definition of critical components. It's emphasizing these AI-optimized parts, like the specific AI chips, the HBM, advanced sensors.
Right.
And this implies increasing specialization across the entire supply chain. It points towards a future hardware landscape that's likely more fragmented, with lots of diverse component types.
Tailored for specific jobs.
But also highly optimized for diverse AI workloads. We're moving away from a one-size-fits-all approach to computing hardware.
Okay, this massive demand and the strategic importance of it all must mean the semiconductor industry itself is undergoing a huge metamorphosis, beyond just building more chips.
It absolutely is. Source 6 describes AI not just as a market opportunity, but as a fundamental strategic imperative. For semiconductor companies to maintain relevance and competitiveness going forward, they have to embrace AI. It's forcing them to rethink pretty much everything they do.
And the industry roadmaps, the plans for future development, they're reflecting this.
Yes, very clearly. Key industry roadmaps, like the Microelectronics and Advanced Packaging Technology Roadmap, or MAPT, that outlines the path for the industry from 2023 out to 2035, they're explicitly shaped by AI's demands.
AI is a central theme.
Absolutely. Sources 3 and 12 show AI as a central driver, pushing for huge advancements in raw computing power, memory capabilities, data interconnection performance, how fast you can move data between chips, and even new packaging technologies to put different specialized chips closer together for better performance.
And these roadmaps are really important.
They're vital. They guide billions and billions of dollars in R&D investment, capital expansion for building new multi-billion-dollar fabs, and they essentially dictate the technological direction of the entire global ecosystem.
Okay, let's look at some of the key players then, and their specific strategies or contributions in this AI-driven era. NVIDIA is obviously central here, right?
NVIDIA continues to be a dominant force, yeah. They keep setting the benchmarks for AI training and inference performance with their GPU architectures like Hopper and the recently announced Blackwell platform. Source 3 points this out clearly.
But it's not just the main processor.
No, beyond the core GPU, they're also pioneering crucial supporting innovations. Things like high-speed photonic switches using light for networking and co-packaged optics, which integrate optical communication right onto the chip package.
Why is that important?
It's essential for addressing the critical networking and data movement bottlenecks inside these massive AI data centers. As the models get bigger and the data traffic explodes, moving data efficiently becomes just as important as processing it.
Okay, what about Intel? They have such a long history across many types of processors. How are they positioning themselves now?
Intel is heavily engaged across various AI hardware fronts. Source 4 mentions their significant development work in neuromorphic computing, that brain-inspired approach we touched on.
Right, the Loihi chip.
Exactly. They have the Loihi research chip, its successor Loihi 2, and their Halo Point system, based on Loihi 2, which Source 4 cites as the world's largest neuromorphic system built to date. It features over 1.15 billion artificial neurons.
Wow.
They also contribute significantly to developing and optimizing the AI algorithms that run on their more traditional CPUs and other accelerators. They're playing across the board.
And TSMC, the world's leading contract chip manufacturer, the foundry giant. They don't design chips, but they make them for everyone.
TSMC is absolutely crucial. As the leading foundry, they're responsible for actually manufacturing the most advanced AI chips designed by many of the big, fabless semiconductor companies. Companies that design chips but don't make them.
Like Apple, NVIDIA.
Exactly. Key partners like Apple, NVIDIA, AMD. Sources 3, 17, and 18 highlight this. Their ability to reliably produce chips on the cutting-edge process nodes making the smallest, fastest transistors is essential for bringing these incredibly complex AI designs to volume production. Their role is absolutely foundational to the entire ecosystem's ability to scale up AI hardware.
AMD has also made significant moves in the AI space, particularly in competition with NVIDIA.
Yes, AMD has developed a very comprehensive AI roadmap across their product lines, according to Source 19.
And what does that include?
It includes their powerful Instinct MI series GPUs, which are specifically designed for data center AI workloads, directly competing with NVIDIA's offerings. Their ePYC server CPUs increasingly incorporate dedicated AI acceleration capabilities. And importantly, they're actively promoting an open software platform called ROCm.
Why open software?
It's meant to provide an alternative ecosystem for AI development, challenging NVIDIA's CDA dominance and hopefully fostering broader adoption of AMD hardware in the AI space.
Okay, and ARM. Historically known for mobile and edge devices where power efficiency is king. How are they adapting to this AI wave?
ARM is focusing heavily on enabling AI specifically at the edge and in embedded systems, exactly where that power efficiency is critical. Source 21 describes their extensive portfolio of power-efficient IP. That's the core designs they license out to other chip makers.
What kind of IP?
It includes things like their Corestone subsystems for secure embedded AI, their widely used Cortex-A CPUs, and their Ethos NPUs neural processing units designed specifically for efficient AI inference right there on the device. Their IP makes it easier for companies to integrate AI processing into everything from smartphones and wearables to IoT devices and automotive systems.
So it sounds like success in this era isn't just about who can build the single fastest general-purpose chip anymore. It's more complex.
Exactly right. Source 3 and 6 really emphasize this new competitive dynamic. While access to leading-edge manufacturing knows that the ability to make the tiniest, most powerful transistors is still incredibly important for raw performance. Software capabilities are becoming equally important differentiators. We're talking about the AI algorithms themselves, the AI-driven EDA tools used to design the chips more effectively, the complex software stacks needed to run AI efficiently on the hardware.
Right.
Success now is about much more than just raw silicon. It's about smarter design processes, building resilient and agile supply chains, implementing highly efficient manufacturing. And all of these are increasingly being underpinned by AI itself.
So this shift could potentially reshuffle the industry leadership over the next decade. If the traditional giants don't adapt quickly enough to this software and systems view.
That's a definite possibility, yeah. The game is changing.
And all this intense focus, the massive investment, the strategic importance, it also has a significant geopolitical dimension, doesn't it?
It absolutely does. Source 1 and 7 highlight how the massive global investment in AI chip production and the sheer strategic importance of these AI accelerators are fueling intensified geopolitical competition among major global powers. And it's heightening concerns everywhere about supply chain sovereignty, security, and resilience.
Why is AI hardware suddenly so tied to national security and economic power in this new era? It used to be just components.
Source 7 makes it really clear. AI capabilities are increasingly seen as integral to both economic competitiveness and national security in the 21st century. Reliable, domestic, or at least secure access to cutting-edge AI hardware, and crucially, the ability to design and manufacture it is now seen as a fundamental strategic imperative for nations. This elevates semiconductors from being seen as commodity components to truly strategic assets.
And this is where initiatives like the U.S. CHIPS Act and the European Chips Act come into play, right, to boost domestic production.
Precisely. Source 22 explains that these initiatives represent concerted efforts by governments to significantly increase their domestic semiconductor manufacturing and R&D capacity. They explicitly aim for what they call technological sovereignty and diversifying semiconductor manufacturing hubs to reduce dependence on any single region or supplier, particularly East Asia.
So a global push.
It's a global push, driving massive investments in building new fabs in multiple countries. But it could also potentially lead to a more fragmented and perhaps less economically efficient global manufacturing environment. Compared to the highly specialized global supply chain we have today, there are trade-offs.
And that AI devours chip supply dynamic we mentioned earlier just makes these geopolitical concerns even worse, I imagine.
Source 23 confirms this directly. The immense demand for AI chips, especially those made on the leading-edge processes, is creating supply constraints that are definitely exacerbating these geopolitical concerns.
How so?
Well, nations see the supply crunch. They worry about access for their own industries and security needs. This dynamic could potentially lead to more protectionist trade policies, more stringent export controls targeting specific technologies or countries,
Right.
or even escalate into what some commentators are calling chip wars as nations compete fiercely for technological supremacy and supply security, potentially using trade policy as a weapon.
Okay, so beyond the market structure and geopolitics, AI is also impacting the semiconductor value chain itself, like every step from sourcing raw materials all the way to shipping the final product.
Yes, Source 6 provides a really good high-level view of this. AI is being integrated across pretty much all the various stages of the semiconductor value chain, from initial R&D and design through manufacturing, supply chain management, all the way to sales and even talent management. The goal everywhere is to improve efficiency, enhance resilience against disruptions, and drive innovation.
How does AI help specifically with something as complex as supply chain management and procurement in this industry?
AI is being rapidly deployed to optimize critical supply chain functions. Source 6 explains it's used for much more accurate demand forecasting by analyzing vast, complex data sets that humans just couldn't process effectively.
Right.
It helps manage inventory levels more effectively, reducing holding costs but also preventing stockouts. It's being used to identify and mitigate potential supply chain risks, like predicting disruptions due to geopolitical events, natural disasters, or even supplier issues. And it analyzes spending patterns to find efficiencies.
Source 24 mentioned something about shifting from just-in-time to predict and prepare.
Exactly. By processing diverse market information, historical data, even news feeds, AI can predict demand with higher accuracy and spot potential disruptions further in advance. This allows companies to shift their strategies from the traditional, highly lean, just-in-time logistics model, which is very vulnerable to shocks, to a more robust predict and prepare model that builds resilience into the supply chain.
So predicting problems before they happen to avoid those costly delays and shutdowns?
Exactly. Moving from being purely reactive to being much more proactive.
Yeah.
And AI is also revolutionizing the semiconductor manufacturing equipment itself and the complex processes run on that equipment.
How so? I mean, semiconductor fabs are already incredibly automated environments, aren't they?
They're marvels of automation. But AI adds a whole new layer of intelligence on top of that automation. Source 25 details this quite well. Machine learning algorithms are processing vast data sets streaming in real time from literally thousands of sensors embedded within the manufacturing equipment.
All that data.
This data allows AI to fine-tune production parameters on the fly, constantly optimizing for quality and yield the percentage of good chips per wafer. It helps reduce waste by identifying potential issues much earlier in the process, and it accelerates time to market by speeding up the optimization of new manufacturing processes. AI significantly enhances automation beyond just simple robotics by adding sophisticated decision-making capability.
And predictive maintenance. That must be incredibly valuable in a fab where a single machine can cost hundreds of millions of dollars.
It's absolutely crucial. Equipment downtime in a semiconductor fab is unbelievably expensive. We're talking potentially millions of dollars per hour of lost production.
Wow.
So AI-powered predictive maintenance systems analyze these continuous sensor data streams, looking at vibration patterns, temperature fluctuations, pressure changes, chemical flow rates, error logs, everything. They anticipate equipment failures before they happen.
So you can schedule maintenance instead of having a catastrophic breakdown.
Precisely. Source 25 suggests this can cut unplanned outages by as much as 30%. And Source 6 mentions that Micron, a major memory manufacturer, reported a 4% enhancement in their overall tool availability, specifically through implementing AI-driven predictive maintenance. That 4% translates into significant production capacity gains.
And defect detection. Can AI actually see things that humans or even older automated optical inspection systems might miss?
Yes. Significantly better in many cases. AI-powered vision systems, often employing sophisticated deep learning models, are achieving defect detection accuracies of up to 99%, according to Source 25. They analyze complex wafer images in real time.
99%.
Their ability to spot subtle anomalies, faint patterns, or microscopic imperfections that might indicate a critical defect often surpasses human capabilities, especially over long periods, and also traditional automated optical inspection methods. They're just better at seeing complex patterns.
Micron had results here, too.
Yeah, Source 6 highlights Micron's result again, a 22% reduction in product scrap, which is huge financially and environmentally, and a remarkable 50% faster resolution of quality issues once they are detected, thanks to AI's role in manufacturing process control and defect analysis.
Okay, this is fascinating. Is AI even helping with the less technical areas like sales and talent management within semiconductor companies?
Source 6 touches on this too. It seems AI is being used to enhance customer segmentation for sales teams, improve lead generation processes, and optimize marketing campaigns to be more effective.
And in HR?
In human resources, AI is streamlining recruitment workflows, sifting through resumes, identifying promising candidates. It's accelerating the time to productivity for new hires by helping personalize their training paths. And it's providing valuable insights into the existing workforce, understanding employee skills, identifying potential skill gaps that need addressing, and guiding future training needs to keep the workforce competitive in this rapidly changing field.
Wow, so AI is truly getting integrated end-to-end across the entire value chain of this massive industry.
It really is. AI is not just consuming electronics anymore. It's fundamentally transforming the industry from the ground up. It's influencing demand, reshaping market dynamics, driving geopolitical considerations, and revolutionizing the operational processes across the entire value chain, from sand to system. It's creating a new level of optimization and automation within the industry itself.
Okay, so AI isn't just consuming electronics. It's fundamentally transforming the industry from demand right through to manufacturing. But how is it changing the very creation of these electronics? This leads us right into Section 2. AI as the designer and fabricator. This sounds like AI is becoming almost a co-creator.
That's a really apt way to put it, yeah. This is perhaps one of the most exciting and rapidly evolving areas we're seeing right now. AI is quickly becoming an indispensable tool in the actual creation of electronic circuits and systems. It's revolutionizing how chips are designed, how their physical layouts are planned on the silicon, how they're fabricated, and how their performance is optimized.
Starting with chip design itself, that's always been an incredibly complex, time-consuming, and labor-intensive process, right? Handled by highly skilled engineers using that sophisticated electronic design automation, or EDA software.
Exactly. And that process is under immense pressure as chips get exponentially more complex. We're talking billions, soon potentially trillions, of transistors on a single chip. Source 26 describes how AI is fundamentally transforming those EDA tools and the methodologies engineers use.
How exactly does AI accelerate these incredibly long design cycles? What does it do?
So AI automates many of the most laborious, highly iterative, and computationally complex tasks within the design flow. There's a groundbreaking example often mentioned, Google DeepMind's work with what they called Alpha Chip.
Right, I remember reading about that.
Source 6 highlights how they demonstrated the ability to reduce the physical design time. That's the crucial, painstaking step of placement and routing, figuring out exactly where every single transistor and wire goes on the silicon wafer.
Which takes ages, normally.
Exactly.
Yeah.
A process that traditionally took expert human engineers weeks or even months. They got it down to mere hours using reinforcement learning.
Hours? That's incredible.
More broadly, AI is credited with reducing overall chip design time by a significant 30–50% across the industry, according to Source 26. It does this by automating tasks like circuit optimization, power analysis, signal integrity checks, and layout fine-tuning.
That's not just a speed up. That fundamentally changes the pace of innovation that's even possible in hardware. Does it also improve the quality of the final design? Thinking about the key metrics, power consumption, performance, and physical area, or PPA.
Absolutely. That's the other major benefit. AI is proving incredibly powerful at navigating the vast multidimensional design spaces involved in chip design to find optimal trade-offs in power, performance, and area. Source 26 notes this explicitly.
How does it do that better than humans?
Humans have great intuition and experience, but AI can systematically explore millions, even billions, of potential design configurations to find the absolute best combination for those PPA targets. Going back to that Google Alpha Chip example, Source 6 says it achieved up to a 6% reduction in total wire length for its TPU designs compared to what human experts achieved.
And shorter wires mean?
Reduced wire length translates directly into better performance because signals travel faster, and also improved power efficiency because there's less capacitance to drive.
Are there other specific PPA improvements cited in the sources from using AI in design?
Yeah, Source 26 provides some additional data points showing the impact. Machine learning algorithms are optimizing power efficiency in specific semiconductor blocks by as much as 40% in some cases, finding clever ways to manage voltage scaling and clock gating.
40%, wow.
AI-driven layout optimization techniques can reduce the physical chip area required by up to 20%. That's critical for fitting more functionality onto a chip or simply reducing the manufacturing cost per chip. And AI-driven circuit optimization is delivering notable 10–15% boosts in maximum clock speed performance by identifying critical timing paths and optimizing them automatically.
Okay, so not only is the design process much faster, but the resulting chips are actually better, more power efficient, smaller, and faster, all thanks to AI assistance. And this must significantly increase the productivity of the human engineers involved.
Yes, absolutely. By automating these repetitive, tedious, and computationally heavy tasks, AI-based EDA tools can improve overall design productivity by a factor of 3x to 5x. That's according to sources 26 and 27.
So it doesn't replace the engineers?
No, not at all.
Yeah.
It frees them up. They can focus on higher-level innovation, architectural decisions, exploring completely new concepts rather than getting bogged down in the painstaking manual optimization of tiny details. It elevates their role.
What about the actual EDA tools themselves that are using AI? Are there specific examples out there?
Yeah, the leading EDA companies are rapidly integrating AI capabilities into their main platforms. Source 3 mentions tools like Synopsys DSO.ai, Cadence Cerebrus, and Siemens EDA platforms. These are becoming standard.
And how do they work? What AI techniques are they using?
Source 27 explains that they often utilize techniques like reinforcement learning. Basically, an AI agent learns optimal design strategies by iteratively interacting with the design environment. It tries different configurations, placements, routing strategies, and then receives feedback based on the resulting PPA metrics. It learns by doing, essentially, but at superhuman speed.
Is this AI assistance limited to just digital chip design? What about the notoriously difficult field of analog IC design? Things like radios, power management chips.
That's a really important point. While AI adoption in digital EDA is definitely more mature because digital logic is more structured and easier to represent mathematically,
Right.
analog IC design is also starting to benefit significantly. Analog design has traditionally relied very heavily on expert intuition, years of experience, and lots of manual tuning.
Kind of an art form.
Almost, yeah. Source 28 discusses applying advanced AI techniques like graph neural networks, GNNs, to model the complex relationships in analog circuit structures. They're using large language models, LLMs, to help interpret design constraints from specifications or even research papers. And they're using things like variational autoencoders, VAEs, to automate complex analog IC sizing tasks.
But it's harder for analog.
It is challenging because analog design involves navigating these highly nonlinear, high-dimensional spaces where tiny changes can have big, unpredictable impacts on performance. But AI is definitely starting to make inroads and provide real value there, too.
Okay, now here's where it gets truly futuristic, maybe even a bit sci-fi. Beyond just optimizing existing designs that humans came up with, the sources mention generative AI is starting to propose entirely new chip architectures. This sounds like AI is actually getting creative.
It's a really significant conceptual step forward, yeah. Source 29 points out that generative AI models are showing real promise in actually conceptualizing and proposing fundamentally new IC architectures and subsystems almost from scratch. Not just tweaking parameters of existing designs, but suggesting novel structures.
How would that even work? Would you just give the AI a high-level goal like, design me a chip that does X?
Exactly, that's the idea.
Yeah.
Generative AI models could potentially be prompted with specific functional parameters, performance constraints, power budgets, target applications.
Okay.
And they could then automatically generate initial chip designs or electronic subsystems based on these high-level requirements. This could potentially slash the intensive upfront engineering effort required for initial architectural exploration and brainstorming. Source 29 highlights this potential quite clearly.
So you could theoretically tell an AI, design me an ultra-low-power chip optimized for real-time object detection on a battery-powered drone. And it might propose a novel combination of processing elements, memory structures, and interconnects specifically for that task.
That's precisely the long-term vision, yes. And generative AI is also being developed to act as sophisticated engineering assistants. Source 29 notes these tools could interpret natural language queries from engineers,
So you could just talk to it.
interact directly with the complex design software environments, provide context-aware recommendations based on the design state, and even automate sequences of design steps. This could significantly boost the productivity of engineers, particularly new ones joining a team. Source 29 even suggests it could potentially double the productivity for new hires by providing intelligent guidance and automating routine tasks. Synopsys is mentioned as actively building these kinds of generative AI capabilities into their tool suites.
There's a specific, really interesting example of this generative AI being used for a unique type of chip architecture mentioned in the sources, related to something called in-memory computing.
Yes, that's LIMCA, stands for LLM, for Automating In-Memory Computing Architecture Design Exploration. Source 30 describes this novel framework. It's driven by large language models.
And what's in-memory computing again?
It's a different computer architecture
Wow.
where the computation happens directly within the memory itself, rather than moving data back and forth between a separate processor and memory. The goal is to avoid that data movement bottleneck, which consumes a lot of time and energy.
Okay, so LIMCA helps design these IMC architectures.
Right. It automates the really complex process of designing and evaluating the specific crossbar architectures used in IMC systems. It explores the design space automatically.
And what kind of results has LIMCA achieved so far? Is it working?
Source 30 reports that LIMCA successfully generated IMC designs for the MNEST classification task that's a common benchmark for image recognition. The generated designs achieved classification accuracy of 96% or greater,
Pretty good.
while maintaining power consumption below 3 watts, which is really critical for these kinds of low-power architectures. The source cites this work as the first published demonstration of LLM-assisted design space exploration, specifically for in-memory computing architectures. It really shows the potential for AI to automate the design of fundamentally new ways of computing.
This also seems like it could potentially democratize chip design to some extent, make it accessible to more people, maybe not just hardcore chip designers.
Source 31 discusses that possibility, yeah. AI-powered design tools, especially those with more intuitive interfaces, perhaps driven by generative AI, could lower the barrier to entry. It might enable individuals with less traditional technical expertise, sometimes called silent designers, or maybe domain experts in a particular field, to translate their conceptual ideas into actual electronic designs.
But it's not quite there yet.
Well, they also note that achieving precise, predictable control over the outcomes of these complex generative tools is still an area of significant ongoing research and development. It's not yet a push-button design solution where anyone can design a complex chip perfectly. There's still a lot of work needed on verification and ensuring reliability.
Okay, so AI is getting deeply involved in designing electronics. What about actually fabricating them? How is AI impacting the incredibly complex process of semiconductor manufacturing itself in the fabs?
AI's impact extends deeply into the fabrication or manufacturing process as well. It's fundamentally improving precision, boosting yield, the number of good chips per wafer, and optimizing equipment maintenance. Source 6 details this quite comprehensively. The fab is where the design becomes a physical reality, and AI is becoming absolutely critical there too.
You mentioned process control and yield optimization earlier when we talked about the value chain. How exactly does AI achieve that in the fab?
AI algorithms are critical for maintaining extremely tight control over the thousands of intricate steps involved in semiconductor manufacturing, depositing layers of material just atoms thick, etching incredibly fine patterns, precisely doping silicon with impurities, and so on.
Right, it's incredibly complex.
Source 6 states AI-driven techniques analyze those massive data streams from the manufacturing equipment in real time to constantly optimize these processes. They ensure higher quality, greater consistency, and greater manufacturing efficiency. All of this directly impacts the yield.
We mentioned Micron's results again.
Right, that 22% reduction in product scrap and 50% faster resolution of quality issues thanks to AI analysis. Source 3 notes that sophisticated ML models analyze subtle patterns in process data to identify deviations and predict potential yield issues before they result in scrapping entire expensive wafers. Source 32 adds that IBM Research is using AI specifically to track down and identify the root sources of microscopic defects during the complex wafer processing steps, which is incredibly hard for humans to do reliably.
And predictive maintenance in the fab environment. Can you reiterate those crucial benefits? Seems especially important there.
Absolutely crucial. In these multi-billion-dollar fabs where equipment is running 247, unplanned downtime is absolutely devastating financially. AI-powered predictive maintenance systems analyze those continuous sensor data streams from lithography machines, etching equipment, deposition tools, looking at vibration, temperature, performance metrics, error logs,
To see trouble coming.
to anticipate equipment failures before they happen. Source 25 says this can cut unplanned outages by up to 30% by allowing maintenance to be scheduled proactively during planned shutdowns, rather than having a machine fail catastrophically mid-production.
Yeah.
Micron reported that 4% enhancement in overall tool availability from this, according to Source 6, which translates directly into significant production capacity gains.
And defect detection. Can AI find flaws that are incredibly small or hard to spot visually?
Yes, with remarkable precision. AI-powered visual inspection systems using advanced deep learning models are achieving defect detection accuracies of up to 99% during real-time analysis of wafer images, as per Source 25.
That's amazing.
They can identify subtle patterns, faint discolorations, or tiny anomalies that might indicate a critical defect that would be nearly impossible for a human operator to consistently spot across millions of transistors or features on hundreds of wafers per day. Their precision and speed surpass previous automated systems and certainly human capabilities at that scale.
Does this AI assistance apply to other parts of electronics manufacturing beyond just the silicon chips, like making the printed circuit boards or PCBs that chips get mounted on?
Yes, Source 33 confirms that AI's benefits are extending across the broader electronics manufacturing landscape, including PCB fabrication and assembly.
How is it used there?
AI is used to optimize the PCB layout itself, helping with component placement and trace routing for better signal integrity. It can simulate and predict potential issues like electromagnetic interference, EMI, before the board is even manufactured. During fabrication, AI can monitor and control the precise deposition of printed layers. And in the assembly stage, particularly for boards with lots of tiny surface-mounted components, AI optimizes the sequences for the pick-and-place machines to reduce assembly time and improve placement accuracy.
Okay, so let me recap. AI is helping design the chips, optimizing their layouts, predicting their performance, helping find the very materials they're made from, controlling the incredibly complex manufacturing steps with high precision, spotting microscopic defects better than humans, and even helping assemble the final products like PCBs.
That's a pretty comprehensive picture, yeah. That's what the sources paint. AI is rapidly becoming an integral, often absolutely necessary, part of the entire electronics creation process, from the initial concept right through to the finished product rolling off the assembly line.
And as we mentioned earlier, this whole cycle increasingly relies on discovering new materials, which AI is also helping to accelerate.
Exactly. That leads us perfectly into AI for materials innovation.
Why is discovering new materials so important for electronics right now? Aren't we doing okay with silicon? And how is AI accelerating this discovery process?
Well, Source 34 explains that new materials are fundamental to continuing the advancement of electronics, particularly as we push the known physical limits of silicon-based technology and explore entirely new computing paradigms that silicon might not be suitable for.
What kind of properties are needed?
We need materials with better properties, maybe higher electron mobility for faster transistors, different magnetic or optical properties for new types of memory or communication, improved energy storage capacity for batteries, maybe even self-healing capabilities for more resilient devices.
And finding these traditionally is slow.
Traditionally, materials discovery is a very slow, often painstaking trial and error process involving lots of experiments. AI is dramatically accelerating this through a field called materials informatics.
Materials informatics, what exactly is that?
It's an interdisciplinary field that leverages AI, machine learning, and advanced data analytics to accelerate the discovery, design, synthesis, and development of novel materials. Source 34 says it's fundamentally shifting materials science, moving it from a purely experimental, sometimes serendipitous process.
Right, like stumbling upon something.
To a much more predictive, data-driven, and targeted endeavor. AI analyzes vast experimental and computational data sets, identifies hidden patterns and correlations between structure and properties, predicts the behavior of hypothetical materials, and suggests promising new compositions or crystal structures for scientists to investigate.
What specific AI techniques are being used in this materials discovery field?
Source 34 mentions a range of techniques are being employed. Graph neural networks, GNNs, are particularly useful for modeling the complex relationships within atomic structures. Physics-informed neural networks, PINs, are interesting because they incorporate known physical laws directly into the AI model, making its predictions more accurate and physically realistic.
And generative AI, like for images.
Yes, generative AI approaches, similar to those used for image or text generation like diffusion models, are being used to propose entirely new material compositions and crystal structures based on desired target properties.
And the applications of these AI-discovered materials in electronics, where would they be used?
They're seen as crucial for pushing performance boundaries across the board. Applications include finding materials for next-generation semiconductors that might eventually move beyond silicon, finding materials for high-temperature superconductors, which could revolutionize computing or energy transmission, developing improved materials for advanced energy storage solutions, like better batteries for portable electronics and electric vehicles, and finding novel materials for highly sensitive sensors or other critical electronic components. The goal, as noted in sources 36 and 34, is identifying materials with optimized efficiency, durability, and unique performance characteristics tailored for specific electronic applications.
Are there any notable examples of AI actually discovering or helping develop new materials that have been reported recently? Is this real yet?
Yes, there are some really exciting proof of concepts emerging. Source 37 highlights Microsoft's MatterGen project. It uses generative AI, specifically diffusion models, to design novel, stable materials essentially from scratch, based purely on desired properties you specify.
How does it work?
It was trained on a massive data set of over 600,000 known stable materials. MatterGen can propose entirely new crystal structures by intelligently adjusting the elements involved and their positions within the crystal lattice. An example mentioned is a predicted material with novel properties, TAC 206.
That's remarkable, designing a material just by specifying the properties you want. Any other examples?
Source 38 discusses AI-powered search engines that use pre-trained GNNs. These successfully identified 50 previously unknown candidate materials belonging to a recently discovered class called ultramagnets.
Ultramagnets.
Yeah, they have unique magnetic properties. The AI identified potential metals, semiconductors, and insulators in this class, and these predictions were later confirmed by detailed physics-based calculations. Source 39 adds that AI is also used in the manufacturing process for some of these new materials, for instance, analyzing complex RHED patterns during the growth of 2D semiconductors for real-time quality control.
What are the biggest challenges in using AI for materials discovery for electronics right now? It sounds promising, but what are the hurdles?
Source 34 and 35 point out some significant hurdles, primarily related to the data itself. Datasets in material science are often sparse, meaning there are many more possible materials than known ones we have data for. They're high-dimensional, as material properties depend on many complex variables. They can be biased, reflecting historical research focus areas, and they're often noisy due to inherent experimental inaccuracies.
So the data isn't perfect.
Right. Overcoming this requires not just more advanced AI algorithms, but also crucially bridging the expertise gap between materials, science domain experts, and data scientists. You need people who understand both fields deeply.
Okay, so AI-driven materials discovery is critical for future electronic advancements, especially beyond silicon, but it's still a challenging frontier.
Exactly. And this capability circles right back and reinforces the importance of that PPA optimization, power performance, area, and chip design that we talked about earlier. AI's ability to navigate those incredibly complex multidimensional design spaces during chip layout and optimization is absolutely crucial for finding the optimal balance of power, performance, and area. It explores trade-offs across potentially billions of options, something human designers simply cannot explore exhaustively within a reasonable time frame. Source 26 really emphasizes this profound optimization capability.
It sounds like when you integrate AI across design, materials, and fabrication like this, you're creating a kind of comprehensive digital twin environment for electronics development.
The sources definitely describe this emerging reality. Source 33, 2, 6, and 25 all mention how the deep integration of AI into EDA tools, manufacturing equipment control systems, and materials simulation capabilities is fostering an environment akin to a comprehensive digital twin ecosystem for electronics.
So you can model everything virtually first.
Essentially, yes. This allows for extremely detailed simulation of chip behavior, precise prediction of potential manufacturing outcomes based on chosen process parameters, and iterative optimization of the design in a purely virtual space before any physical silicon is actually fabricated or materials are synthesized.
What are the benefits of that?
AI's capacity to simulate complex PCB behaviors, predict potential manufacturing defects, optimize circuit layouts for PPA in this virtual environment, and then manage the physical fabrication in real time based on these digital models. It means the entire electronic product lifecycle, from initial concept through design, manufacturing, and even predicting reliability in the field, can be virtually modeled, tested, and refined with exceptional fidelity.
So fewer mistakes, faster time to market.
Exactly. It drastically reduces costly design errors or manufacturing hiccups, significantly shortens time to market, and importantly, it enables engineers to explore more radical or unconventional design ideas with much greater confidence because they can be thoroughly vetted and de-risked in the digital realm first.
And the future of generative AI in design. Is it truly moving towards more autonomous creativity beyond just optimization?
The sources suggest this trajectory is definitely beginning. Source 30 and 29 reiterate that AI is moving from primarily optimizing designs created by humans to potentially proposing entirely novel circuit architectures or system concepts autonomously, based just on high-level functional requirements, like that LIMCA example for in-memory computing design we discussed.
So the human role changes.
In this potential future, the human role shifts. It moves away from detailed schematic drawing or layout towards defining those high-level specifications, rigorously validating the AI-generated proposals, managing the crucial ethical and security implications of the AI's output, and essentially curating the best, most innovative results that the AI produces.
That could potentially unlock architectural innovations that human designers, relying on their experience and intuition, might not naturally arrive at.
That's the exciting potential, yes. It could unlock entirely new architectural spaces. And this capability is deeply, deeply interdependent with that AI-driven material science we just talked about.
How are they linked so tightly?
AI-driven materials discovery is absolutely critical for enabling the specialized AI hardware and the entirely new classes of electronic devices. We're starting to discuss things that go fundamentally beyond traditional silicon, like practical neuromorphic chips, scalable quantum computers, or highly advanced sensors. Source 36 and 34 highlight this critical link. Progress in these novel hardware areas is often gated or limited by the availability of suitable materials that possess the exact right combination of electrical, thermal, magnetic, or quantum properties. AI-accelerated material science provides the essential building blocks.
But it depends on getting the materials science right.
Yes. Source 34 notes that success here depends heavily on overcoming those data challenges we mentioned, and also fostering a new generation of interdisciplinary experts who truly understand both material science and data science. Fundamentally, these novel computing paradigms often need both novel materials and novel AI control systems for their effective operation and scaling.
This is a very deep and multi-layered integration. It's really hitting home that AI isn't just running on electronics anymore. It's helping to imagine, design, and create them from the ground up.
It is rapidly becoming a fundamental co-creator in the entire electronics ecosystem. It's a profound shift.
Okay, so AI is becoming a co-creator of electronics, but it's also enabling entirely new ways of actually doing computation itself, really pushing the boundaries of what's possible with computing paradigms maybe inspired by biology or physics, or focusing heavily on adaptability and resilience. This takes us right into Section 3, Emerging AI-Driven Computing Paradigms.
Exactly. This is where we see some of the most radical shifts in how computation might be performed in the future. It's all driven by the fundamental need to go beyond the inherent limits of traditional computing architectures, especially von Neumann architecture, to meet AI's ever-growing demands for performance and efficiency.
And these new paradigms promise what?
They promise to potentially transcend current limits in areas like energy efficiency, the complexity of problems we can solve, or the resilience and longevity of systems. Sources 4, 14, 45, 49, and 52 all touch on these exciting emerging developments.
All right, let's start with neuromorphic computing. The sources describe it as brain-inspired. What does that actually mean in a technical sense? How is it different?
It's a fundamental shift in the underlying computer architecture. It's inspired directly by the structure and function of the biological brain. It moves away from that traditional von Neumann architecture, which has physically separate processing and memory units connected by a bus. Source 4 and 14 explain this well. Neuromorphic chips aim to mimic biological neural networks much more closely in silicon.
What are the core principles they use to do that?
Well, they often emulate biological neural networks using something called spiking neural networks, or SNNs.
Spiking.
Yeah, where information is processed and transmitted through discrete spikes or electrical pulses, similar to how biological neurons communicate. It's primarily event-driven processing computation, only happens when a spike arrives at a neuron, which makes it inherently very efficient for certain types of tasks where activity is sparse.
Okay, what else?
Crucially, it often involves the co-location of memory and processing units. Sometimes this is called in-memory computing or compute in memory. This minimizes the significant energy and latency penalties associated with constantly moving data back and forth between separate components, which is a major bottleneck in traditional systems. Source 14 adds that information isn't just represented by the value of a number, but can also be encoded using temporal dynamics, like the precise timing or the frequency of these spikes.
What are the main advantages of this brain-inspired approach compared to the traditional chips we use now?
The primary, a potentially very significant advantage, is unparalleled energy efficiency, especially for specific types of AI tasks, things like pattern recognition, anomaly detection, and processing sensory data in real time.
How much more efficient?
Source 4 and 14 state that neuromorphic systems can be orders of magnitude. We're talking potentially hundreds or even thousands of times more energy efficient than conventional AI accelerators like GPUs for these specific tasks.
Thousands of times. Wow.
This makes them incredibly well suited for power-constrained environments. Think edge devices, IoT nodes operating on small batteries, always-on sensors.
Right.
They also offer potential advantages in enabling real-time learning capabilities directly on the chip. And their structure has a certain biological plausibility which might be beneficial for applications like robotics or advanced brain-machine interfaces.
Who are the key players developing these technologies? Is this still mostly research, or are there actual products?
It's moving from research towards early commercialization. Source 4 mentions Intel has been a pioneer in neuromorphic research for years with its Low-E research chip and its more advanced successor, Low-E 2.2.
And that Halo Point system.
Right. Intel's Halo Point system, based on Low-E 2, is cited as the world's largest neuromorphic system built so far, integrating over 1.15 billion artificial neurons and capable of 1.15 trillion synaptic operations per second. IBM also developed early neuromorphic chips like TrueNorth and is exploring architectures like North Pole, focusing on efficient in-memory AI, potentially for cloud-based applications as well. Source 14 mentions BrainChip actually offers a commercial neuromorphic processor called Akida, targeted specifically at low-power edge AI, and large research projects like Spinnaker 2 in Europe are developing neuromorphic supercomputing platforms.
What kind of applications could this ultra-energy efficient brain-like computing enable in the future if it takes off?
Source 14 and 43 list a really diverse and exciting range of potential applications. Think highly energy-efficient autonomous robots that can process sensor data and make decisions in real time without draining their batteries.
Okay.
Real-time healthcare diagnostics running on portable or wearable devices, more sophisticated brain-machine interfaces potentially, enhanced cybersecurity systems that can detect subtle anomalies in network traffic much faster and with less power, complex pattern recognition tasks in scientific data streams, and even optimizing energy use and communication routing in complex systems like satellite constellations.
What are the major challenges holding neuromorphic computing back from more widespread adoption right now? It sounds great, but what's the catch?
Well, Source 40 points out that the fundamental computational models, these SNNs, are very different from the deep neural networks used in mainstream AI today. This requires developing entirely new training algorithms specifically tailored for spiking networks, things like spike timing dependent plasticity, STDP, or methods called surrogate gradients. It's not straightforward.
So the software side is tricky.
Yes, and Source 42 emphasizes the critical need for developing user-friendly software tools, compilers, and open programming frameworks that allow developers who are familiar with traditional AI tools like TensorFlow or PyTorch to easily program and deploy their applications onto this very different neuromorphic hardware. Right now, it still requires very specialized expertise. It's a steep learning curve.
Is there a market for this technology emerging yet, despite the challenges?
Source 14 projects significant growth for the neuromorphic computing market, forecasting a strong 21.2% CGR in the coming years. This projected growth is fueled by that increasing demand for hyper-efficient AI solutions, the rapid expansion of edge computing and IoT where power is paramount, and the development of autonomous systems that require real-time, low-power intelligence. So the potential is definitely recognized.
Okay, next up on the list of emerging paradigms, quantum hardware integration for AI. This sounds incredibly advanced, almost bordering on science fiction.
It certainly is pushing the boundaries significantly, yeah. Source 45 discusses the immense promise of combining the unique computational power of quantum computing with the pattern-finding strengths of AI. The goal is to tackle problems that are currently considered intractable, meaning fundamentally impossible to solve in any reasonable time frame, even for the most powerful classical supercomputers we have or can imagine building.
How does quantum computing offer an advantage specifically for AI tasks? What can it do better?
Quantum mechanics has these weird but powerful principles, like superposition, where a quantum bit, or qubit, can be both 0 and 1 at the same time, and entanglement, where qubits are linked regardless of distance. These allow quantum computers to perform certain types of computations exponentially faster than any classical computer. Source 45 explains this potential speedup is particularly relevant for specific classes of AI and optimization tasks.
Like what kind of tasks?
Things involving complex optimization problems like finding the absolute best solution among a truly vast number of possibilities, which comes up a lot in logistics, finance, and material science. analyzing large-scale data sets where the relationships are incredibly complex or the amount of data grows exponentially, and sampling from complex probability distributions, which is a core operation in many machine learning algorithms.
So are we talking about a whole new field called quantum machine learning, or QML?
Yes, that's exactly the emerging field. Source 2 describes QML as the active research area focused on developing specifically quantum algorithms that can accelerate machine learning tasks.
What would that look like?
This includes developing quantum versions of classical algorithms, like quantum support vector machines, or exploring entirely new possibilities with quantum neural networks. The potential impact is significant. Possibly much faster model training, improved accuracy for certain types of complex problems, and the ability to work with exponentially larger feature spaces than classical AI can handle. This could potentially revolutionize areas such as natural language processing, computer vision, and especially complex scientific simulations like drug discovery or designing new materials at the atomic level.
Are we at the stage yet of building full, large-scale, fault-tolerant quantum computers specifically designed for AI?
Not yet, no. We're still quite far from that. Source 46 explains that the near-term focus, which is where most current efforts and investment are concentrated, is on developing hybrid quantum classical systems.
Hybrid, meaning they combine quantum and classical computers.
Exactly. These systems integrate the current generation of noisy intermediate-scale quantum processors, or QPUs, with powerful classical high-performance computing HPC resources, like clusters of GPUs and CPUs.
How do the classical and quantum parts work together in such a hybrid system? What does each part do?
Source 46 clarifies this division of labor. The classical computing resources handle the tasks that they are good at, and frankly, that quantum computers aren't suited for yet. This includes preparing the input data for the QPU, generating the precise sequences of microwave or laser pulses needed to control and manipulate the qubits, reading out the probabilistic results from the quantum computation,
Okay.
then post-processing those results to get a meaningful answer. Crucially, the classical computers also handle extremely complex procedures like quantum error correction decoding, which is essential to mitigate the high noise levels inherent in current quantum systems. And, very importantly, they often use classical AI for the calibration and optimization of the quantum processor itself.
Wait, so classical AI is helping to build, tune, and run the quantum computer, which will then potentially help run other, maybe different types of AI faster. That's another one of those feedback loops.
Exactly. It's a fascinating layer of interdependence. AI and machine learning are becoming crucial tools for actually developing and operating these early quantum computers. They're used for simulating quantum phenomena to better understand qubit behavior, for designing novel quantum algorithms, for optimizing the precise control pulses needed to manipulate qubits with high fidelity, and even for improving the overall performance of the quantum system using techniques like reinforcement learning running on those powerful classical superchips connected to the QPU. Source 46 details this tight coupling.
Are there any examples of these hybrid quantum classical systems being developed by companies right now?
Yes, Source 46 mentions the NVIDIA DGX quantum system. This is a collaboration between NVIDIA and a company called Quantum Machines. It integrates Quantum Machines' specialized OPX1000 quantum control platform directly with NVIDIA's powerful GH200 Grace Hopper superchips. The key is achieving the ultra-low latency communication needed between the classical control system and the quantum processor to run complex hybrid algorithms effectively.
What are the potential killer applications for this quantum-accelerated AI once it matures?
Source 45 lists several areas where the potential speedup could be truly transformative. Accelerating the discovery of new drugs and materials is a big one, finding optimal molecular structures for catalysts, designing novel self-healing materials, accurately predicting chemical reactions or material properties like corrosion resistance.
Right, things that are really hard to simulate classically.
Exactly. Optimizing extremely complex financial models and risk assessments. Improving the accuracy and speed of climate modeling, which involves massive simulations. And enhancing solutions to complex optimization problems in logistics, supply chain management, or network design.
Who are some of the leading players in this global race to build quantum hardware and integrate it with AI?
It's a mix of big tech companies and specialized startups. Source 48 points to Microsoft's significant investment in developing its Majorana 1 chip, which is based on a novel topological qubit architecture they hope will lead to more stable and inherently error-resistant qubits. Source 46 mentioned the NVIDIA Quantum Machines collaboration on hybrid systems. Source 4 notes that Google and IBM are also major players at the forefront, developing various types of quantum processors like superconducting qubits or trapped ions, and actively exploring quantum machine learning algorithms and hybrid approaches, plus many well-funded startups.
What are the biggest challenges holding back widespread practical quantum AI computing? It sounds amazing, but why isn't it here yet?
Source 4 and 48 state clearly that practical, fault-tolerant quantum computing is still very much in its nascent stages, its early days. Building stable, scalable quantum hardware with a sufficient number of high-quality qubits that maintain their quantum state long enough to compute, and implementing robust, efficient error correction mechanisms is a monumental scientific and engineering challenge. It requires overcoming fundamental physics hurdles and incredibly difficult engineering problems. Widespread use for solving real-world problems beyond specialized research is likely still years, maybe decades away.
Okay, let's shift gears to another emerging paradigm mentioned, self-adaptive and self-healing electronic systems. This sounds like electronics that can detect damage and maybe even fix themselves.
Yes, this is all about building inherent resilience, robustness, and longevity directly into electronic systems. It's particularly important for systems that need to operate reliably for long periods in harsh, remote, or critical environments where failure is not an option, and human intervention might be impossible or too slow. Source 49 explains that AI is a key enabler for creating systems designed to autonomously adapt to changing conditions, detect damage or faults as they occur, and even initiate repair processes with minimal or no human help.
What's the core concept behind these systems? How do they work?
The idea is to design systems with internal sensing, diagnosis, and repair capabilities built right in from the start. They need to be able to identify and diagnose hardware problems, software glitches, or even physical damage, and then automatically take steps to resolve the issue, maintain functionality, and minimize downtime. Source 49 covers this core concept.
And how does AI play a crucial role in making this self-healing capability happen?
AI algorithms are absolutely essential for interpreting the continuous stream of data coming from various sensors embedded throughout the system. They analyze this data to detect anomalies, identify patterns indicative of degradation or damage, and precisely locate the source of the problem. Source 49 gives a really compelling example from the field of soft robotics.
Soft robotics, like squishy robots.
Exactly. In this example, AI monitors subtle changes in the electrical properties of a network of liquid metal microdroplets embedded within the robot's soft, stretchable elastomer skin. By analyzing how the resistance or capacitance changes, the AI can detect and accurately localize damage, like a puncture or a high-pressure impact point on the robot's body.
Okay, so it finds the damage, and then the repair process. How does AI manage that?
Once the AI detects and localizes the damage, it can then trigger and manage onboard localized repair mechanisms. Following that soft robotics example from Source 49, the AI can activate specific parts of that same liquid metal network, but this time using it as tiny, localized Joule heating elements.
So it heats up the damaged area.
Exactly. This localized heat can then reprocess and effectively heal the specific type of polymeric material the robot's skin is made from, sealing the puncture or damage autonomously.
That's amazing. What about predictive maintenance and anomaly detection in more conventional self-healing systems, like, say, personal computers? Is that happening?
Source 50 mentions that self-healing capabilities are starting to be incorporated into modern PCs, though maybe in a less dramatic way than physical repair. Here, AI analyzes telemetry data constantly collected from components like solid-state drives, SSDs, hard disk drives, HDDs, or thermal sensors inside the computer.
What's it looking for?
It's looking for patterns that predict potential hardware failures, like signs an SSD is wearing out, or a cooling fan is about to fail, or detecting software glitches before they cause a system crash or data loss. This allows the AI to trigger proactive steps.
Like what?
Like automatically reallocating data from a failing drive sector to a healthy one, adjusting cooling fan speeds or processor clocks to manage thermals, or initiating system recovery modes to minimize downtime and prevent catastrophic failure. It's about anticipating problems.
Are there other real-world examples or applications being developed beyond soft robotics and PCs?
Source 51 describes the development of self-healing electronic skin, or e-skin. This is a flexible material designed for wearables or robotics that can recover over 80% of its electrical functionality within just 10 seconds after being cut or damaged without needing any external stimuli like heat.
And AI is involved there too.
Yes. AML algorithms are used to analyze the data collected from this self-healing e-skin for wearable applications, like measuring muscle strength or identifying muscle fatigue in athletes or patients, achieving high accuracy over 95%. It shows how the material resilience is paired with intelligent processing of the sensor data. Source 49 emphasizes again that self-healing capabilities are particularly crucial for robots operating in dynamic, unpredictable, or hazardous environments. Think search and rescue robots, planetary exploration rovers, or industrial robots in dangerous settings where physical damage is highly likely and sending a human for repairs is difficult or impossible.
What are the underlying technologies that actually enable these self-adaptive and self-healing systems? It sounds like a mix of things.
It's definitely a convergence of multiple advanced technology fields. It requires sophisticated sensor networks deeply embedded throughout the system. It needs advanced diagnostic AI algorithms capable of interpreting complex sensor data in real time. It needs automated repair mechanisms integrated directly into the hardware or materials themselves. And critically, it relies on significant innovation in materials science to create these responsive materials, things like self-healing polymers, conductive liquid metals, shaped memory alloys, and other smart substances. Source 49 connects all these enabling technologies.
Okay, one more emerging paradigm to discuss.
Right.
How is AI impacting reconfigurable hardware? Things like FPGAs and maybe that newer concept of reconfigurable intelligent surfaces, or RIS.
AI is profoundly influencing both the design and the real-time use of reconfigurable hardware. This type of hardware, which has the unique ability to change its function or internal structure on the fly after it's been manufactured, is becoming increasingly important for handling the dynamic and diverse nature of modern AI workloads, particularly in edge computing and real-time applications where flexibility is key. Source 52 highlights this trend.
How do FPGAs, field programmable gate arrays, enable adaptive AI specifically?
FPGAs offer the ability to dynamically adapt their hardware resources and the specific logic circuits implemented on them after deployment. Source 52 says this dynamic reconfigurability can lead to significant gains in energy efficiency, reduced latency, and higher throughput for specific edge and real-time AI tasks compared to using fixed-function ASICs, which are very efficient but inflexible, or general-purpose processors, which are flexible but less efficient.
Is this related to something called dynamic partial reconfiguration?
Yes, exactly. Source 52 specifically mentions dynamic partial reconfiguration, or DPR. This advanced technique allows specific regions or blocks of an FPGA to be reconfigured with new logic at runtime without stopping the operation of the rest of the chip. Frameworks like DRA, mentioned in the source, leverage DPR along with hardware-software co-design methodologies to efficiently map and adapt different AI models onto the same FPGA hardware over time, as needed.
What does DPR enable?
Source 54 explains that DPR enables things like flexible resource allocation, using only the hardware needed for the current task, and advanced optimization techniques like variable bit width processing. You can adjust the precision of calculations dynamically based on the specific AI model being run, saving power and computational resources when lower precision is sufficient.
And FPGAs are being used to accelerate specific complex AI algorithms effectively.
Source 52 confirms this. FPGAs are being widely used now to accelerate various deep learning algorithms like convolutional neural networks, CNNs, commonly used in computer vision, and increasingly complex graph-based models like GC and YOLO by implementing the necessary parallel processing structures directly in the flexible hardware fabric.
Which companies are focusing heavily on using FPGAs for AI acceleration?
Source 20 specifically mentions AMD, which significantly expanded its capabilities in reconfigurable hardware through its major acquisition of Xilinx, the longtime FPGA market leader. AMD now offers a broad portfolio of FPGAs and adaptive SoCs, like their Versal series, that are specifically designed and marketed for accelerating AI inferencing across a whole range of applications, from massive data centers down to demanding embedded systems and even niche areas like space applications where radiation tolerance and in-flight reconfigurability are critical advantages. Conferences like ISFPGA regularly showcase the ongoing advancements in using FPGAs for AI acceleration. Source 55.
Okay, what about that newer concept, reconfigurable intelligent surfaces, or RIS? How does AI fit in there? That sounds different from FPGAs.
It is different. Reconfigurable intelligent surfaces involve large physical surfaces, maybe deployed on buildings or walls, composed of many small electronically reconfigurable elements. Think of them like programmable mirrors, but for radio waves instead of light.
Programmable mirrors for radio waves. What do they do?
They can manipulate electromagnetic waves intelligently. Source 56 explains that AI systems are absolutely crucial for managing these RIS panels effectively. AI algorithms, often using machine learning, deep learning, or reinforcement learning, dynamically adjust the phase shifts of each individual element on the surface in real time. They do this based on complex factors, like the surrounding environment, the location of mobile users, current network traffic patterns,
Yeah.
all to intelligently steer and optimize wireless communication signals. This is seen as incredibly important for boosting coverage, capacity, and reliability in complex urban environments, or for enabling future communication technologies like 6G. The AI is constantly adapting the surface to the changing radio environment.
It really seems like AI is driving hardware itself to become much more flexible, almost programmable at a very fundamental level, kind of like software-defined hardware.
That's a profound observation, and it's a key trend that Source 59 highlights quite strongly. As AI itself continues to evolve towards more complex and dynamic systems, think agentic AI, systems that can make decisions and act autonomously in the world, or physical AI, robots interacting directly with the physical environment.
Right.
The computational workloads they generate become increasingly heterogeneous, unpredictable, and rapidly changing. Future silicon hardware will likely need to be much more codable or reconfigurable than traditional fixed architectures, just to keep pace with the demands of these advanced AI systems.
How might that vision of codable hardware actually look in practice?
Source 59 envisions future systems built not just from single monolithic chips, but perhaps from diverse chiplets, small, specialized blocks of silicon optimized for specific functions like logic processing, different types of memory, sensing, or communication. These chiplets would be integrated tightly together, maybe in 3D stacks, and interconnected by a highly dynamic network on chip that AI itself could control.
So the AI manages the connections.
Yes, this intelligent network could rapidly steer data streams and reconfigure the connections between these specialized supercells or chiplets on the fly, adapting the hardware's overall functionality almost instantaneously to match the specific needs of the current AI workload. This kind of flexible, disaggregated architecture would also make it easier to integrate emerging memory technologies or incorporate custom hardware designs, perhaps using open standards like RISC-V into the system.
Why are all these different, quite radical computing paradigms, neuromorphic, quantum, self-healing, reconfigurable, emerging now, seemingly all at the same time? What's driving this?
Source 60 and 4 synthesize this well. It's fundamentally a quest driven by necessity. We're trying to overcome the inherent physical and architectural limitations of traditional computing as we know it.
Like Moore's law slowing down.
Exactly. We're hitting practical limits with CMOS scaling. Making transistors ever smaller is getting harder and more expensive. And we're constantly battling the von Neumann bottleneck, that fundamental energy and time cost associated with constantly shuffling data between separate processing and memory units in traditional architectures. These limits are becoming critical bottlenecks, precisely because of the exponential increase in computational demands driven by modern AI.
So each paradigm targets a different bottleneck.
In a way, yes. Neuromorphic computing primarily targets extreme energy efficiency for specific AI tasks. Quantum AI integration targets solving problems with complexity far beyond classical reach. Self-healing systems target reliability, resilience, and longevity, especially in harsh environments. Reconfigurable hardware targets adaptability and efficiency for dynamic, diverse workloads. Source 14, 45, 49, and 52 each highlight these distinct advantages in target applications.
And these new paradigms also heavily rely on the AI-driven materials science and the AI needed for control that we discussed earlier, don't they? It all seems connected.
Absolutely. Source 34, 46, and 56 reinforce this crucial interdependence layer. Novel computing paradigms often rely on exotic materials or materials with precisely engineered properties that may not exist naturally or haven't been manufacturable at scale before. This makes AI-driven materials discovery a critical enabler for their physical realization.
And the control aspect.
Furthermore, effectively controlling these incredibly complex systems, managing thousands of qubits in a quantum computer, dynamically optimizing billions of phase shifters on an RAS surface, or orchestrating intricate self-repair processes in real time relies heavily on sophisticated, often AI-based control algorithms. These novel paradigms frequently need both novel materials and novel AI control systems for their effective design, operation, stability, and scaling.
It's fascinating how much intelligence is being embedded not just on the hardware, but increasingly in the hardware itself, the ability to sense, diagnose, reconfigure, even self-repair.
Source 49 touches on this intriguing aspect. Systems that can sense their own state and environment, diagnose internal issues, reconfigure their own architecture dynamically, or even heal physical damage, begin to exhibit characteristics we traditionally associate more with biological organisms or perhaps sophisticated software agents, rather than inert hardware.
It's blurring the lines.
It is increasingly blurring the traditional lines between hardware and software. It points towards a future of potentially dynamic, adaptive, perhaps even living technological systems.
These new paradigms are incredibly exciting and really point towards a future where hardware is much more dynamic, efficient, and capable than ever before. But as you said, they seem intrinsically linked to how hardware and software are co-developed, particularly as we try to push this intelligence outside the massive data centers.
That's exactly right. This coevolution and the tight integration between hardware and software are what's creating this powerful distributed intelligence we're starting to see. And that brings us neatly into Section 4. The coevolution of hardware and software, and the rise of edge AI.
This feels like where the rubber meets the road, the practical reality of how this whole AI revolution is getting integrated into the actual devices and systems that surround us every day.
It really is the bridge from the advanced research labs and hyperscale data centers out into the real world. Source 62 emphasizes that hardware and software in this AI era are just no longer isolated silos developed independently. They are inextricably linked in a deep reciprocal relationship.
How so?
AI algorithms and the specific workloads they generate are profoundly shaping how hardware is designed and architected. And conversely, breakthroughs in hardware are constantly enabling entirely new types of AI capabilities and applications that weren't possible before. We see this synergy everywhere now, particularly in these AI-optimized system-on-chip designs and embedded systems, and especially fueling the rapid growth of edge computing.
Okay, let's talk about those AI-optimized system-on-chip, or SoC architectures first. How has AI changed the fundamental approach to designing these incredibly complex integrated circuits that power things like smartphones?
Traditionally, SoC design focused primarily on integrating diverse functions. CPUs, GPUs, memory controllers, various communication interfaces, peripherals onto a single piece of silicon, with the main goals being maximizing integration density and optimizing the overall power, performance, and area, PPA. Source 62 explains that AI is fundamentally altering both the priorities and the methodologies used in this complex design process.
How does AI directly influence the SoC design process itself? Is it just about adding an AI core?
It's much more than just adding a core. Source 62 states that AI algorithms themselves, machine learning, deep learning, reinforcement learning, are now becoming integral tools used within the SoC design process. Engineers are using AI to help optimize a multitude of incredibly complex design parameters that are really beyond efficient manual human capability at this scale.
Like what kind of parameters?
This includes optimizing the physical layout of potentially billions of transistors to minimize wire length and congestion. Deciding how different resources like CPUs, integrated GPUs, dedicated neural processing units, NPUs, and other custom accelerators are allocated, partitioned, and interconnected on the chip. And fine-tuning complex power consumption profiles and clocking strategies, all specifically optimized for the target AI workloads that the SoC is intended to run efficiently.
Can AI automate parts of this architecture design?
Yes, reinforcement learning models, for example, can automate the process of exploring billions of potential configurations for different functional blocks and interconnect topologies to find the most efficient architecture for a given set of target AI tasks constraints.
So AI is helping decide not just the physical layout, but the actual architecture, what processing elements are included, and how they talk to each other on the chip based on what AI tasks it needs to run well.
Exactly. It's optimizing the entire system architecture for AI, using AI tools to do it. And a key feature of these modern AI-optimized SoCs is the integration of those dedicated AI hardware accelerators directly onto the chip.
Right, the dedicated AI cores alongside the traditional CPU and GPU.
Precisely. Source 2 mentions that specialized processors or hardware blocks like TPUs, NPUs, or other custom AI accelerators are now commonly integrated into modern SoC designs, particularly for mobile devices, consumer electronics, automotive systems, and other edge devices.
And what's the benefit of having them right there on the SoCs?
These accelerators are specifically architected for high throughput and low latency execution of common AI tasks, things like image recognition, natural language processing, or simple decision-making models directly on the chip itself, without needing to send data off to a separate power-hungry component or all the way to the cloud for processing.
Okay, and what about the communication on the chip itself? With so many complex processing blocks and potentially high-speed data movement needed for AI, that must become a significant bottleneck if it's not designed correctly.
It absolutely does. The on-chip communication fabric, typically known as the network on-chip or NOC, is absolutely critical for ensuring that data can move efficiently and quickly between all the different processing cores, accelerators, memory blocks, and peripherals integrated onto that single piece of silicon. Source 63 explains that AI and machine learning techniques are now being used to help design and manage these increasingly complex NOCs.
Is there an example of that?
Yes. For instance, a company called Arteris offers smart NOC IP called FlexGen. It uses ML heuristics to automate the generation of complex NOC interconnects. It optimizes their topologies specifically for the different data traffic patterns characteristic of various AI workloads. And they've shown results like reducing total wire lengths by up to 30% and minimizing data latencies by 10% or more compared to traditional manual design methods.
Why is this AI-assisted approach needed for designing the NOC now? Can't humans just do it?
Source 63 notes that the sheer complexity of high-end SOC designs today, especially those optimized for diverse and demanding AI workloads with maybe dozens of different processing elements, now often surpasses the capabilities of traditional manual human design and optimization for the on-chip network. AI can explore and find optimal solutions in design spaces that are simply too vast and complex for humans to navigate effectively within project timelines.
Okay, moving beyond those complex SOCs and phones to the more ubiquitous embedded systems, the processors hidden inside our appliances, cars, industrial equipment, medical devices. How is AI infusing intelligence into those?
Embedded systems, which are found in virtually everything electronic around you, are getting significantly smarter and more capable through AI integration. The design of these systems is inherently a hardware-software co-design problem from the start.
Why co-design?
Because you typically have very tight constraints on performance, cost, physical size, power consumption, and often strict real-time responsiveness requirements. Source 64 emphasizes that meeting all these conflicting constraints effectively requires concurrently designing the hardware architecture and the software that runs on it. They have to be developed together. And AI is driving new and more effective approaches to this critical co-design process. Source 65.
And this co-design approach is enabling more AI processing directly on the embedded device itself, not relying on the cloud.
Yes, exactly. Integrating AI capabilities directly within the embedded processors found in devices like smart speakers, wearables, smart home hubs, or industrial sensors enables real-time analysis and decision-making on the device itself. Source 2 points out that this on-device AI processing, often called edge AI, is crucial for several reasons.
What are the benefits?
It reduces dependency on constant cloud connectivity, which isn't always available or reliable. It significantly enhances responsiveness by eliminating network latency critical for real-time control. It improves data privacy and security by keeping potentially sensitive data local instead of sending it to the cloud. And it enables devices to operate autonomously, even if the network connection is lost or intermittent.
Companies like ARM seem central again here, providing the building blocks for this edge and embedded AI, right?
Yes. Source 21 notes that ARM is a key player in providing the foundational IP, the licensed core designs, for many of these AI-enabled embedded systems. Their comprehensive portfolio includes energy-efficient Cortex-A CPUs, those specialized Ethos NPUs designed for AI inference on devices, and integrated Corestone subsystems that bundle processing, security features, and AI acceleration together. These are all specifically designed to strike that difficult balance between needing sufficient AI performance and meeting the critical constraints of low energy consumption, especially in battery-powered or thermally sensitive devices.
And academia is focusing heavily on this hardware-software co-design aspect for AI deployment, too. It's not just industry.
Source 66 confirms this strongly. Academic research is increasingly focusing on developing systematic methodologies and tools for efficiently deploying complex deep neural networks, DNNs, onto various resource-constrained hardware platforms. The key is considering both the hardware architecture limitations and the software implementation details concurrently during the optimization process.
Are there examples of this in practice?
They even mentioned that specialized accelerators developed by large tech companies like Google's TPU and Meta's MTIA chip were actually designed from the very beginning with specific software frameworks and target AI workloads in mind. This really highlights the industry trend towards extremely tight hardware-software co-design, specifically for optimizing AI performance and efficiency.
This leads perfectly into AI's influence on the broader Internet of Things, IoT hardware landscape, and the whole concept of edge computing. It sounds like we're seeing a significant architectural shift in where intelligence actually resides in these networks.
This is arguably one of the biggest architectural evolutions being driven by AI in recent years, yes. Source 67 states unequivocally that AI processing the need to analyze data and make decisions quickly and locally is the primary driver for moving away from traditional cloud-centric IoT architectures.
Where all the sensor data just got sent to the cloud.
Exactly. where raw data was typically collected by dumb sensors and shipped off to massive cloud data centers for processing. Now we're moving towards edge computing, where significant data processing and AI inference happens much closer to the source of the data, either right on the device itself or perhaps in local gateways or edge servers nearby.
What are the biggest benefits, again, of processing that AI data right there at the edge instead of in the cloud?
Source 67 lists the critical advantages which are driving this shift. Localizing the intelligence dramatically reduces latency. That's essential for real-time control loops in things like autonomous vehicles, industrial robotics, or even augmented reality applications.
Okay, low latency. What else?
It conserves often limited or expensive network bandwidth because you're only sending processed insights or alerts back to the cloud, not huge streams of raw sensor data. It significantly enhances data privacy and security by processing sensitive personal or operational data locally without transmitting it over the network where it could be intercepted. And as we mentioned, it enables devices to operate autonomously, making local decisions even in environments with limited or intermittent network connectivity.
But achieving this requires new types of components, right? Ones with local compute strength but still low power.
Exactly. The hardware in typical IoT devices needs a fundamental upgrade to handle these AI workloads effectively. Implementing AML at the device level means IoT hardware designers must include capable compute components like those NPUs or maybe smaller micro-NPUs specifically for accelerating AI inference. They need sufficient on-device memory to store the AI models and intermediate data. And they need sophisticated hardware-software integration to make it all work together efficiently within tight power and cost budgets.
So microcontrollers are getting smarter.
Yes. Source 67 explains that traditional microcontrollers are evolving rapidly, now often incorporating dedicated AI cores. And more complex IoT devices are utilizing sophisticated sockets that feature heterogeneous processing units specifically designed for handling different aspects of the AI workload efficiently.
And there are specialized hardware accelerators appearing just for the more demanding edge AI tasks, beyond just integrated cores.
Absolutely. There's a growing market for dedicated edge AI accelerators. Source 70 mentions prominent examples like Google's Edge TPUs, NVIDIA's Jetson platform, which is very popular for robotics and embedded vision AI, and ARM's Ethos NPUs, Source 21, which are licensed widely for power-efficient inference.
Others too.
Other major players include Qualcomm with their Snapdragon AI processors found in countless smartphones and other edge devices, Source 4, and companies like Microchip offering FPGAs, such as their MPF100TL, which provide flexible low-power compute options for specific industrial or communications edge segments, Source 1. These are all designed to deliver high-performance AI inference under the tight power and thermal constraints common at the edge.
Is even generative AI, the really big models, starting to move out of the massive data centers and towards the edge? That seems computationally challenging.
Source 69 notes this is a newer, but definitely significant, emerging trend. We're seeing concerted efforts now to bring generative AI capabilities onto advanced smartphones and PCs. Initiatives like Microsoft's Copilot Plus PCs and Apple's recently announced Apple Intelligence are prime examples.
What's the goal of running generative AI locally?
The goal is to leverage local processing for tasks that benefit from low latency, enhance privacy by keeping personal data securely on the device, and the ability to personalize or adapt the models via fine-tuning based on local user data and context. This trend is also extending towards potentially implementing generative AI capabilities on more powerful edge devices like next-generation robotics platforms or autonomous vehicles.
But how do you actually get those massive, complex machine learning models, which are typically trained in giant cloud data centers with thousands of GPUs, onto these much smaller, resource-constrained edge devices?
That's a huge challenge, and Source 68 discusses ongoing research into optimization paradigms specifically for this problem. It's often referred to as the data model system triad.
What does that involve?
It involves concurrently optimizing the AI model itself, using techniques like quantization, reducing numerical precision, pruning, removing unnecessary connections, or knowledge distillation, training a smaller model to mimic a larger one, optimizing the data representation and flow, and optimizing the underlying hardware and software system on the edge device to execute the resulting reduced or optimized model as efficiently as possible. It's a multi-pronged optimization problem.
How does this push for more processing at the edge influence the overall architecture and design of IoT devices beyond just adding an AI chip? Does it change other parts?
Yes. Source 69 suggests it influences the entire device architecture significantly. Edge AI devices need robust support for both local processing and potentially standard web or cloud protocols for tasks like receiving model updates from the cloud or sending aggregated insights back. They require increasingly robust and reliable communication capabilities, leveraging technologies like 5G and looking ahead towards 6G for higher bandwidth and lower latency.
What about security?
Enhanced security features become absolutely paramount due to the distributed nature of Edge AI and the potential for processing sensitive data locally. This includes things like hardware roots of trust built into the silicon, strong encryption for data at rest and in transit, and secure boot processes. And for more complex edge devices managing multiple AI tasks, there's potential for using containerization or virtualization technologies to isolate different applications and improve manageability. Source 67 adds that modular and flexible hardware architectures are becoming more important, allowing manufacturers to more easily customize devices based on the specific edge AI applications and performance requirements.
You mentioned the key companies enabling Edge AI earlier, like ARM, NVIDIA, Intel, Qualcomm, Microchip. Let's just quickly reiterate their central role in making this shift happen.
Right. Source 21 really highlights ARM's foundational role through its comprehensive IP portfolio and its strong focus on hardware-software co-design, including their collaborations with companies like Meta on software frameworks such as Executorch, which aims to make deploying AI models onto ARM-based devices much more accessible for developers. Source 70 mentions NVIDIA's powerful Jetson platform, which has become almost a de facto standard for developers working on robotics and embedded vision AI applications. Source 4 notes Intel's broad range of processors and FPGAs that can be adapted for various edge AI workloads. Qualcomm, as mentioned, holds a dominant position in mobile and consumer edge AI with their widely used Snapdragon platforms. Source 4. And Source 1 points to companies like Microchip offering specialized FPGAs tailored for specific industrial or communication edge segments that require flexibility and very low power consumption. It's a diverse ecosystem.
This whole push for distributing intelligence out to the edge seems to be a significant driver for that trend towards heterogeneous integration and specialization in chip design that we discussed earlier. It all connects.
That's a critical connection to make, yes. As AI workloads become incredibly diverse, some tasks needing massive parallel floating point calculations like GPUs are good at, others needing super efficient integer math like NPUs excel at, others needing rapid sequential processing like traditional CPUs provide, and still others needing high bandwidth memory access or specific sensor interfaces achieving optimal efficiency demands, combining these different specialized processing units intelligently onto a single chip or within a single package. Source 62 emphasizes this strong trend towards heterogeneous integration. Different AI tasks simply need different kinds of compute, and putting them all together optimally requires very sophisticated design methodologies.
And AI itself helps design these increasingly complex, heterogeneous systems, right?
Yes. Source 62 reiterates AI's crucial role in designing these highly complex, heterogeneous software. It cites that Arteris FlexGen Smart NoC example, Source 63, again as a prime case where AI is automating and optimizing the critical communication infrastructure needed to connect these diverse processing elements efficiently. This really reinforces the point that the future of silicon is likely moving away from relying solely on single monolithic general-purpose chips towards more integrated application-specific platforms built from a combination of specialized components tailored for the task.
And at a broader, almost global level, this push for edge AI is creating a new kind of distributed computing fabric, changing the whole internet architecture.
Exactly. Source 67 explains that the push for edge AI is effectively creating a vast, distributed, intelligent global computing fabric. It's fundamentally shifting the balance of computation away from being purely centralized in massive cloud data centers towards a much more decentralized model, where significant processing happens locally on potentially billions of devices spread across the edge of the network.
What are the implications of that?
This offers those key advantages in latency, privacy, and bandwidth conservation. But it also requires developing and deploying new network technologies, like the advancements being explored for 6G, to handle the massive connectivity and data rates. It demands new security paradigms specifically designed for highly distributed and potentially less trusted environments.
Yeah.
And it necessitates new data governance models for managing data that's being generated, processed, and stored across this vast, decentralized network.
This tight integration between the hardware and the software, especially for AI applications, really sounds like hardware-software co-design is becoming the default methodology now, not just an occasional exception for specialized projects.
Source 64 confirms this perspective strongly. This tight coupling of demanding AI workloads, specialized hardware accelerators, and highly optimized software stacks is making hardware-software co-design the default, necessary methodology for developing complex AI-driven systems, particularly in the embedded and edge domains. Source 64 states that concurrent optimization of both the hardware architecture and the software implementation is simply essential for meeting today's aggressive performance, power, and cost targets.
What does that demand from the industry?
Source 72 adds that this shift demands new types of electronic design automation, EDA tools that explicitly support these co-design flows, allowing hardware and software teams to work together more effectively. It requires advanced simulation environments that can model the interactions between hardware components and software execution. Comprehensively, they mention the Panorama platform as an example, Source 72. And perhaps most importantly, it demands engineers who possess a more holistic understanding, bridging the traditional gap between hardware and software design principles. You need people who can think about the whole system.
Okay, this coevolution of hardware and software is clearly creating powerful distributed intelligence that's getting embedded deeper and deeper into more and more of our environment. But this incredibly rapid transformation must come with significant challenges and potential pitfalls that we absolutely need to address, both as an industry and maybe as a society.
Absolutely. The path forward isn't simply one of smooth, inevitable technological progress. It's filled with hurdles, complexities, and risks that require very careful navigation. And that brings us to our final section, Section 5, Navigating the Transformation Challenges and the Path Forward.
All this rapid change, the intense investment, the huge strategic importance we've discussed, it must inevitably lead to some potential disruptions and significant challenges. What are the big ones?
It does. The sources highlight several key areas of potential disruption and major challenge. First and foremost, we have ongoing market dynamics and really significant supply chain stress. The sheer, almost unprecedented demand for advanced semiconductor chips, and especially high-bandwidth memory, HBM, driven primarily by AI applications, is straining global supply chains, sometimes, frankly, to their breaking point. Source 23 vividly describes this phenomenon with the headline, AI devours chip supply.
How significant is this strain on the supply chain, really?
Source 23 notes that demand for AI servers alone is projected to grow at a staggering 40–50% AGR in the coming years. That level of focused demand consumes a disproportionate amount of the world's advanced manufacturing capacity, particularly at the leading-edge nodes needed for the most powerful AI chips. But it also puts pressure on more mature nodes needed for supporting components like power management ICs or display drivers.
So it could crowd out other sectors.
Yes, there's a real risk it could crowd out demand from other important sectors like automotive or industrial, leading to significant shortages, longer lead times, and price volatility across the broader electronics market.
And this uncertainty is starting to impact confidence among chip buyers and industry players.
Yes, it seems so. Source 23 reports a noticeable decline in buyer confidence regarding supply chain resilience for the near future. In a recent survey, only 65% of semiconductor industry leaders expressed confidence about securing adequate supply in 2025. That's a significant drop from 82% who felt confident the previous year. And notably, 42% of these leaders specifically expect shortages in advanced manufacturing nodes, which are absolutely critical for producing those cutting-edge AI chips.
And this ties back directly to the geopolitical factors and the push for technological sovereignty we discussed earlier.
It absolutely does. Source 7 emphasizes again that AI capabilities and the underlying semiconductor technology are now absolutely central to geopolitical competition and national strategy. The intense global competition for AI hardware access and this strong desire for technological sovereignty are driving nations to implement trade barriers, tariffs, and export controls.
What's the risk there?
These policies risk fragmenting the highly optimized, efficient global supply chain that's been built over decades into potentially less efficient, perhaps segregated, east-west technological ecosystems. Source 22 points to initiatives like the U.S. CHIPS Act and the European CHIPS Act as prime examples of governments pouring billions into boosting domestic sovereignty and supply chain resilience. While the goal of resilience is understandable, it could inadvertently lead to a less globally efficient, potentially more expensive manufacturing environment overall.
And there also seems to be this fundamental mismatch in the pace of innovation between the AI software, which moves incredibly fast, and the hardware development cycle, which is much slower.
Source 59 calls this out as a critical challenge, yeah. AI software algorithms and models are evolving at an incredibly rapid pace. Major breakthroughs or shifts in dominant model architectures can happen in mere months, sometimes even weeks. Hardware development, on the other hand, Designing the chip, verifying it, ramping up manufacturing still takes years, typically.
What's the danger of that mismatch?
This desynchronization creates a significant risk of what's called stranded assets. Hardware designs or even entire multi-billion-dollar manufacturing facilities could become suboptimal, or in the worst case, effectively obsolete by the time they are ready to enter the market, simply because the state-of-the-art in AI technology shifted dramatically during the long hardware development cycle. It makes long-term investment decisions very risky.
Okay, beyond these market disruptions and supply chain issues, the increasing power and autonomy of AI tools in the actual design and manufacturing processes also raise some significant ethical considerations, don't they?
These are hugely important considerations that the industry and society as a whole must grapple with very carefully. Source 73 highlights several significant ethical questions swirling around things like algorithmic bias potentially creeping into designs, complex issues of intellectual property ownership for AI creations, and the fundamental security of systems designed or optimized by AI.
How can algorithmic bias actually show up in something like chip design or manufacturing? That seems abstract.
Source 73 explains it quite well. The AI tools used for tasks like selecting materials based on predicted properties, optimizing circuit layouts, or controlling sensitive manufacturing equipment are all trained on vast data sets. These data sets often reflect historical outcomes, past engineering decisions, and even implicit human biases.
So the AI learns the biases.
If these training data sets contain biases, for instance, if certain materials or design approaches were historically favored due to factors not purely related to technical merit, or if the defect detection training data is skewed towards common defects and misses novel ones, then the AI tool can inherit or even amplify these biases in its recommendations or actions.
What's the result?
This could potentially lead to suboptimal designs for certain applications, perpetuate existing inefficiencies, or even result in manufacturing processes that have blind spots, perhaps being less accurate at detecting defects on novel materials if the AI wasn't adequately trained on them. Source 75 mentions guidance being developed, like NIST Special Publication 1270, which specifically addresses how to identify and manage bias in AI systems.
What about intellectual property? When AI is generating potentially novel designs or proposing new materials, who owns that?
Source 76 raises these complex and frankly currently unresolved legal questions about intellectual property, IP ownership, for designs or materials that are significantly generated or discovered by AI systems. Who owns the IP? The user of the AI, the developer of the AI. Can an AI itself even be listed as an inventor on a patent? The laws weren't written with this scenario in mind.
Are there other IP risks?
There's also a significant risk of unintended copyright or patent infringement if the AI models are trained on proprietary datasets without proper authorization, or if their generative process inadvertently replicates elements of existing protected designs. Source 76 and 77 note that the legal landscape here is evolving very rapidly, and companies operating in this space need extremely clear contracts regarding IP ownership and robust monitoring systems to manage these risks.
And what about security concerns? Could hardware that's been designed, at least in part, by AI be less secure?
Source 78 warns that AI-driven design optimizations, while potentially improving performance or power, could also inadvertently introduce subtle vulnerabilities or even hide malicious backdoors if the verification validation process isn't comprehensive enough to fully understand the complex decisions the AI made during optimization.
And AI could be used maliciously.
Furthermore, AI itself is inherently a dual-use technology. Sophisticated AI tools could potentially be used by malicious actors to deliberately synthesize harmful code, design hardware trojans, or create targeted attacks aimed at disrupting semiconductor supply chains. Source 79 emphasizes the critical need for robust, secure development lifecycle practices, rigorous verification and validation processes specifically tailored for AI design components, and continuous monitoring of deployed hardware for unexpected behaviors. Source 80 mentions relevant IEEE 7000 series standards that are being developed to address ethical considerations, including security in the design of autonomous and intelligent systems.
What about accountability and transparency? If an AI makes a critical design choice or controls a manufacturing step and something goes wrong, who's responsible? Especially if the AI is a black box.
That's a huge challenge. Source 76 points out that many advanced AI models, particularly complex deep learning systems used in optimization or control, can function essentially as black boxes. It can be extremely difficult, sometimes impossible, to fully understand why the AI made a specific design choice, or why a particular manufacturing error occurred if the process was directed by an opaque AI algorithm.
So accountability is difficult.
This lack of transparency makes it incredibly challenging to assign accountability when things go wrong, or even just to learn from mistakes effectively. There's a growing demand in the AI field for explainable AI, XAI techniques, that can provide insights into the AI's internal reasoning or decision-making process, but applying these techniques effectively to the hyper-complex domains of hardware design and manufacturing is still very difficult.
And then there's the broader risk of misuse of these incredibly powerful AI capabilities enabled by all this advanced hardware.
Source 76 acknowledges this difficult reality. The same powerful AI hardware and software that enables incredibly beneficial applications like accelerating medical diagnostics, advancing scientific discovery, or optimizing energy grids can also be misused. It can be used to create highly realistic deepfakes for misinformation campaigns, generate sophisticated phishing attacks, automate malicious cyber activity at scale, or potentially enhance the capabilities of autonomous weapon systems. These broader societal risks underscore the profound need for careful consideration of how this powerful technology is developed, governed, and deployed.
It really sounds like navigating this volatile environment, the market pressures, the geopolitical fragmentation, these deep ethical challenges requires a lot more than just brilliant technical expertise.
It absolutely does. Source 79 makes a compelling point that for companies operating in this high-stakes AI electronics space, ethical considerations are rapidly moving beyond being just a matter of basic compliance or risk mitigation. They are becoming a potential source of competitive advantage or, conversely, significant disadvantage. As AI becomes increasingly autonomous in designing and fabricating critical infrastructure components, the provenance, integrity, and fairness of these AI-driven processes become absolutely paramount for building and maintaining trust with customers, partners, and the public. Source 79 argues convincingly that prioritizing ethical development, transparency, and responsible deployment builds that essential trust, while failures in these areas like biased designs or security breaches traced back to AI tools can cause significant and lasting damage to a company's reputation and bottom line.
This rapid and fundamental transformation must also require a significant evolution in the workforce, right? The skills needed to work in this industry must be changing dramatically.
Absolutely. That's another major challenge highlighted across the sources. Source 5 points out that the AI revolution sweeping through electronics is creating massive demand for entirely new skill sets and simultaneously exposing a significant global talent gap that could become a major bottleneck limiting future growth and innovation.
Is there specific data on the scale of this projected talent shortage?
Source 5 provides some pretty concerning projections. The U.S. semiconductor industry alone is projected to face a shortfall of around 67,000 skilled workers, including technicians, computer scientists, and engineers by the year 2030. Globally, the demand for additional skilled workers needed across the semiconductor and related AI hardware field could exceed 1 million by that same year.
1 million workers.
This shortage of qualified personnel is seen as a critical constraint on the industry's ability to innovate, expand manufacturing capacity, and meet the torrid pace of demand being driven by AI.
What kind of skills are most needed in this evolving landscape? Is it just about hiring more AI experts?
Source 5 suggests it's more complex than that. The future workforce needs a sophisticated blend of skills. It's not just about having traditional semiconductor expertise. You still need people with deep knowledge of device physics, material science, lithography, manufacturing processes, circuit design principles. But crucially, they now also need a strong foundation in AI-related skills.
Like what specifically?
Like machine learning concepts, understanding generative AI models, data science techniques, proficiency with using these new AI-driven EDA tools, and strong software development skills, including languages like Python, which are ubiquitous in AI workflows.
And non-technical skills.
Beyond these core technical skills, Source 5 also emphasizes the growing importance of broader abilities, like complex problem-solving, creativity and innovation, critical thinking to evaluate AI outputs, and effective communication skills, essentially, the skills that allow humans to work effectively alongside these increasingly intelligent and autonomous AI tools.
Can AI tools themselves help address this talent gap somehow? Maybe by making existing engineers more productive or helping with training?
Yes, there's some hope there. Source 6 mentions that AI tools are already being used within semiconductor companies to help streamline recruitment processes, for example, analyzing resumes more efficiently. They can help accelerate the time to productivity for new hires by providing personalized training modules and intelligent guidance. And AI analytics can provide valuable insights into the existing workforce's skill sets, identifying potential gaps, and helping target training programs more effectively. Source 5 notes that online AI platforms are also facilitating large-scale upskilling and reskilling initiatives to help bring the existing workforce up to speed on new AI-related techniques and tools.
But addressing this huge gap long-term seems like it requires more fundamental changes, maybe starting right back in the education system.
It really does seem to require that. Source 5 argues convincingly that it's not just a quantitative shortage of engineers, but fundamentally a skills composition problem. We need more people with these interdisciplinary capabilities that blend traditional engineering disciplines with data science and AI expertise.
So education needs to change.
Source 5 also stresses the need for a concerted, collaborative effort involving academia, industry, and government to revamp education and training systems. Source 7 specifically mentions the need to strengthen the STEM pipeline, all the way from K-12 through university. It calls for revamping university STEM curricula to deeply integrate AI and data science principles across engineering disciplines. And it highlights the importance of fostering strong industry-academia partnerships, citing examples like the University of Michigan's Maverick program, Source 82, which focuses specifically on advanced semiconductor manufacturing workforce development.
And lifelong learning.
Source 6 adds that fostering a culture of continuous lifelong learning within the industry is absolutely essential, given the pace of change. This might be supported by things like industry-recognized micro-credentialing programs, professional certifications in AI-related skills, and maybe even personalized AI-powered learning platforms that adapt to individual needs and career paths.
Okay, one more major challenge area. Sustainability. Given the enormous energy demands of training and running AI models and the resource intensity of semiconductor manufacturing, the environmental impact must be a growing concern.
Yes, the environmental footprint of this rapidly expanding AI electronics ecosystem is definitely a growing concern, and it's highlighted in the sources. Source 83 and 6 point squarely at the high energy consumption associated with both training and operating large AI models. Training a single state-of-the-art model can consume megawatts of power for weeks or months. Data centers housing vast numbers of AI servers are becoming significant contributors to global electricity demand and carbon emissions.
And manufacturing itself.
And Source 25 highlights that semiconductor manufacturing itself is an incredibly resource-intensive process. It requires substantial amounts of energy, vast quantities of ultra-pure water, a wide range of chemicals, some hazardous, and inevitably generates significant waste streams that need careful management.
But is there a paradox here? Can AI also help with sustainability efforts within the industry?
Yes, that's the interesting paradox and potentially a crucial part of the solution. Source 25 notes that AI technologies are also proving to be powerful tools for enabling sustainability improvements within the semiconductor industry itself.
Wow.
AI can be used to optimize energy consumption in the fabs by more accurately predicting and managing power loads for different processes. It can help reduce material usage and waste by improving process control and increasing manufacturing yields, meaning fewer scrapped wafers. AI-powered systems can optimize logistics and supply chains to reduce transportation energy. Source 84 mentions that smart manufacturing initiatives and the use of comprehensive digital twins, both heavily enabled by AI, are explicitly aimed at optimizing complex production processes for greater resource efficiency and a reduced overall environmental footprint.
What about designing more eco-friendly hardware right from the start? Is that happening?
Yes, there's definitely a growing focus on that. Source 3 and 36 point to increasing research and development efforts aimed at designing inherently more energy-efficient AI chips, getting more computations per watt. And there's a growing interest in exploring the use of more eco-friendly and potentially recyclable materials in electronics manufacturing, moving away from some of the more problematic substances used historically.
Any specific technologies helping here?
Source 85 mentions emerging technologies like silicon photonics, which uses light pulses carried over optical waveguides instead of electrical signals on copper wires for data movement within and between chips, as offering significant potential for building more scalable and much more energy-efficient AI hardware compared to traditional electronic GPUs, especially for large-scale data center applications. This could help address the escalating energy demands of AI infrastructure.
Okay, navigating all these incredibly complex challenges, the market stress, the geopolitics, the profound ethical dilemmas, the critical talent gap, and the pressing sustainability concerns, it really sounds like it requires a truly concerted effort and much deeper collaboration across many different players. governments, industry, academia.
It absolutely does. Sources 7, 59, and 79 all strongly underscore this point. Realizing the full positive potential of this flourishing AI electronics ecosystem while effectively mitigating the significant risks requires a coordinated collaborative effort from policymakers, the industry itself, and academic institutions working together. No single entity can solve these challenges alone.
What kind of specific policy actions are needed from governments to foster this ecosystem responsibly?
Source 7 outlines several strategic areas where government action is seen as crucial. Governments need to actively foster domestic innovation and manufacturing capabilities through things like direct incentives for R&D investment, support for chip design startups, and manufacturing investment tax credits, citing examples like the U.S. IRC Section 48D tax credits. They also need to carefully craft trade policies and export controls, ensuring they protect legitimate national security interests without unduly hindering beneficial global collaboration or industry competitiveness. And importantly, the sources suggest this needs to be done with close consultation and input from industry experts who understand the technical and market realities.
And government support for the workforce development we discussed.
Yes. Source 7 calls for significant policy focus on strengthening the entire STEM education pipeline from early schooling onwards. Policies are needed to attract and retain top global talent, including rethinking immigration policies for highly skilled workers. And governments need to support regional partnerships and targeted training programs that connect industry needs with educational institutions effectively.
Investment in the underlying AI infrastructure seems necessary too, beyond just the chips themselves.
Source 7 argues for continued public and private investment in building out next-generation data center infrastructure, optimized for AI workloads, supporting domestic AI server manufacturing capabilities, and investing in other essential hardware infrastructure like high-speed networks. Things like increased federal R&D spending and potentially domestic procurement preferences for government contracts can also play a role in stimulating this critical investment.
What about standardization in this rapidly evolving field? Everything seems to be changing so fast.
Source 59 emphasizes that establishing clear, widely adopted industry standards is absolutely crucial in this environment. This includes standards for AI hardware interfaces, how different chips connect, software APIs, how software interacts with the hardware, data formats for training and inference, and importantly, ethical guidelines for the responsible development and deployment of AI and electronics.
Why are standards so important here?
Standards are vital for ensuring interoperability between components and systems from different vendors, which fosters healthy competition and prevents vendor lock-in. They also accelerate innovation by providing common platforms and building blocks that others can build upon. Source 79 mentions that international organizations like the IEEE are already actively involved in developing both technical standards and ethical guidelines relevant to this space.
And public-private partnerships, are they seen as important?
Yes. Source 7 highlights that public-private partnerships, or PPPs, are essential vehicles for funding large-scale, high-risk, pre-competitive R&D initiatives that individual companies might not be able or willing to undertake alone. They can also help develop shared infrastructure, like advanced prototyping facilities for new chip designs that smaller companies or universities can access. And PPPs are seen as key mechanisms for collectively addressing complex societal challenges related to AI, such as developing best practices for sustainability or ensuring the ethical and equitable deployment of AI technologies.
It really seems that navigating the complex ethical landscape, the global sustainability concerns, and the sheer technical complexity of these new systems requires a truly global perspective and much deeper international collaboration, not just isolated national efforts.
Source 59 and 79 strongly reiterate this critical point. Unilateral approaches by individual nations to setting technical standards or defining ethical rules for AI in this globally interconnected industry are inherently risky. They can lead to technical incompatibilities that stifle innovation, create new security vulnerabilities at the interfaces between different systems, hinder beneficial trade and collaboration through fragmentation, and potentially result in an inequitable distribution of the benefits and risks of AI technology worldwide.
So collaboration is key.
Collaboration on developing international standards, shared ethical frameworks, and joint research initiatives is seen as absolutely critical for building global trust, ensuring responsible innovation pathways, and collectively addressing challenges like climate change or pandemic response that are inherently global in nature and where AI can play a huge role.
This has truly been a deep dive into what feels like a profoundly transformative area of technology. It touches everything.
It really has. It's clear from the sources that AI isn't simply influencing electronics anymore. It's fundamentally redefining every single aspect of it, from concept to deployment.
Right, from how the most basic components are designed and manufactured, all the way to enabling completely new ways of computing that seemed like science fiction, and pushing that intelligence right out to the very edge of the network where we interact with it every day.
It's driving unprecedented levels of growth and innovation across the board. It's leading to highly specialized hardware tailored for specific tasks, dramatically accelerating design cycles, and enabling electronic systems that are more adaptive, more resilient, and in some cases, even capable of healing themselves.
But as we've spent a good amount of time discussing, this incredible journey isn't without its significant challenges. We have to carefully navigate serious supply chain strains and intense geopolitical competition. We need to grapple with complex ethical dilemmas around bias, fairness, intellectual property, and security. We absolutely have to address a critical global talent gap, and we must manage the growing environmental footprint of both AI computation and electronics manufacturing.
The sources make it incredibly clear, I think, that the future of electronics isn't just going to be AI-powered. It's increasingly going to be AI-designed, AI-optimized, AI-manufactured, and perhaps even AI-maintained. Sources 29, 6, 25, and 49 all point strongly towards this inescapable trajectory.
This really points towards a future that looks like a highly automated, incredibly adaptive, maybe even a self-evolving technological ecosystem where the electronic systems around us are not just static tools, but potentially dynamic partners in computation, sensing, and interaction.
And successfully realizing this future, while ensuring we harness its immense benefits for all of humanity, really depends on making wise choices now. It requires strategic R&D investment, robust and forward-thinking policy frameworks, essential international collaboration on standards and ethics, and an unwavering commitment from everyone involved to addressing the ethical and sustainability dimensions head-on, not as afterthoughts. The choices we make today in university labs, in corporate boardrooms, and in government policy chambers will profoundly shape the direction of this powerful technological era.
It's certainly a lot to consider as we look at the increasingly intelligent devices that surround us.
It definitely changes how you view your smartphone or your laptop, doesn't it? Knowing what might be coming next and how it's being created.
Absolutely. So maybe a final provocative thought for everyone listening. Consider what it truly means for our relationship with technology when the very hardware around us can not only run incredibly advanced AI, but is increasingly designed, built, and potentially even maintained by AI itself. How does that fundamental shift change our roles as users, as developers, as engineers, and indeed as a society in this rapidly evolving technological landscape?
It fundamentally redefines what it means to interact with, create, and ultimately rely upon technology. The dynamic between humans and machines is shifting in some very profound ways we're only beginning to understand.
A truly provocative thought to mull over as we wrap up this deep dive into the future of electronics and the pervasive influence of artificial intelligence.